Welcome to Venus, the planet that shouldn't exist, or at least shouldn't exist like this. Here's the thing that keeps me up at night. Venus is basically Earth's twin, but hotter and filled with carbon dioxide. Same size, roughly the same mass, formed from the same swirling cloud of cosmic dust about 4.5 billion years ago. If you squinted at the early solar system, you probably couldn't tell them apart. Two rocky worlds sitting side by side in the habitable zone, both getting bathed in warm sunlight. Both presumably with oceans. Both with the same raw ingredients for life. And then something went catastrophically, well, horrifyingly wrong on one of them. By the end of this video, I'm going to tell you exactly what happened. But more importantly, I'm going to tell you why scientists are now genuinely, seriously worried that what happened to Venus might not just be some cosmic accident. It might be a warning, a preview, a ghost of a future we're currently sleepwalking into. And there's one specific number, one measurement taken by a spacecraft in 2020 that changed everything we thought we knew about whether we're alone in the universe. But we'll get to that. Let me back up for a second because I want to tell you about the first time I really thought about Venus. Not as a bright dot in the evening sky, but as a place. An actual physical location with ground and weather and history. I was, maybe 14 years old. My uncle had one of those cheap telescopes, the kind that comes in a cardboard tube from a department store. And one summer evening, he set it up in his backyard and pointed it at what I thought was just a really bright star hanging low in the west. He told me to look through the eyepiece. And there it was. A crescent. Just like the moon, but tiny and glowing this pearly, almost bluish white. I remember standing there in his overgrown lawn, mosquitoes chewing on my ankles, feeling like something had shifted inside my chest. Because that wasn't a light. That was a world, a whole planet with a surface and a sky and, I don't know, weather. And it was showing me phases like the moon does, which meant it was orbiting the sun, and I was orbiting the sun, and we were all just spinning around this ball of fire in the middle of nothing. I didn't sleep well that night. In the best possible way. Anyway, to get back to the point, that crescent I saw wasn't the surface of Venus. It couldn't have been. Because Venus is the only planet in our solar system where you literally cannot see the ground from space with visible light. Ever. Not with the best telescope on Earth, not with the Hubble, not with anything. Because Venus is completely, permanently, 100% shrouded in clouds. Which brings me to the first great mystery. If we can't see the surface, how do we know anything about what's down there at all? Here's the deal. For most of human history, we didn't. Venus was a blank canvas onto which we projected our wildest dreams. And I mean that literally. Well into the 1950s, and I'm not exaggerating here, serious scientists genuinely believed Venus might be a lush, tropical paradise, a jungle world. Some proposed it was covered in swamps full of dinosaur-like creatures. Others thought it might have global oceans of seltzer water, which sounds like a joke, but was a real hypothesis published in real journals. There were even suggestions of a Venusian civilization hiding beneath those clouds. Why did they think this? Because Venus is closer to the sun than we are, so it should be warmer. And because we could see clouds, and clouds on Earth mean water, and water means life. It was a simple, elegant, beautiful line of reasoning. It was also spectacularly, catastrophically wrong. The truth started leaking out in the late 1950s, when radio astronomers pointed their dishes at Venus and picked up something weird. The planet was emitting radio waves consistent with a temperature of around 600 degrees Fahrenheit, which is not a jungle. That's a pizza oven set to broil. At first, people thought it must be a mistake. Maybe the radio waves were coming from Venus's ionosphere, not its surface. Maybe there was some exotic phenomenon we didn't understand. Because the alternative that the surface was actually that hot was too terrible to accept. But then in 1962, humanity did something incredible. NASA launched a small spacecraft called Mariner 2. It was, by modern standards, laughably primitive. It weighed about as much as a large dog. Its computer had less processing power than a modern calculator, and yet this little box of transistors and solar panels flew all the way to Venus and did the first successful close-up scan of another planet in human history. What Mariner 2 found shattered every dream we'd had. The surface temperature wasn't 600 degrees. It was closer to 900. There were no oceans. There was no rain. The atmosphere wasn't nitrogen and oxygen. It was mostly carbon dioxide at a pressure so extreme it would crush a submarine like a beer can. The dream of Venus died on that day in December 1962, and the nightmare began. But here's where things get weird. Because the story of what we did next, of how we actually landed on Venus and what we saw when we got there, is one of the most insane, badass, and completely forgotten chapters in the history of exploration. And when I tell you what those photographs showed, you're not going to believe it. So, the Cold War. I know, we've all heard about the space race. We've all seen the footage of Apollo. We all know Neil Armstrong. But here's what almost no one remembers. While the Americans were laser focused on the moon, the Soviets were fighting a completely different war. They were trying to be the first to touch another planet, and they picked Venus. Between 1961 and 1984, the Soviet Union launched a program called Venera, which just means Venus in Russian. Not a creative name, but communism. They didn't send 1 or 2 spacecraft. They sent 16. 16 missions to a single planet. Most of them failed. Some blew up on the launch pad. Some missed the planet entirely. Some got there and then went silent for reasons we still don't fully understand. But a few, a precious few, made it down. Venera 7 in 1970 became the first human-made object to successfully land on another planet and transmit data back. It survived on the surface for about 23 minutes before being crushed and cooked into silence. Venera 9, 5 years later, sent back the first photograph ever taken from the surface of another world. Not the moon, another planet. And when I first saw that image, when I was in high school going down some late night Wikipedia rabbit hole, I sat there staring at my laptop for a really long time because the image is grainy. It's black and white. It's warped and distorted at the edges. And it shows, of all things, rocks. Just flat, angular rocks scattered across a plane with the horizon curving up on both sides like a fish-eye lens. There's the edge of the lander in the frame. Some of the little instruments sticking out. But it's a photograph from the surface of Venus, taken with a camera that was actively being destroyed by the environment as it took the picture. That camera lasted maybe an hour before the electronics fried, the lens melted, and the whole probe was gently squeezed into scrap by an atmosphere that hates visitors. The Venera landers ultimately gave us our first real look at what Venus is actually like on the ground. And it was, worse than we thought. The surface temperature is around 465 degrees Celsius, or about 870 degrees Fahrenheit. That's hotter than the surface of Mercury, by the way, even though Venus is farther from the sun. Let me say that again because it's genuinely wild. Mercury is basically kissing the sun. It's the closest planet. And yet Venus, which is nearly twice as far from the sun as Mercury, has a surface temperature that's roughly twice as hot. This does not make sense, not intuitively. And it's the first big clue that something extremely unusual is going on. The pressure at the surface is about 92 times Earth's atmospheric pressure. To put that in terms you can feel, that's the pressure you'd experience if you dove about 900 meters below the ocean's surface. Or, if you want a more visceral image, imagine putting an entire full-grown African elephant on top of a coffee mug. That's roughly the force being applied to every square inch of the Venusian ground, at all times, everywhere. The atmosphere itself is about 96.5% carbon dioxide. The remaining 3.5% is mostly nitrogen, with tiny traces of other things. And floating high above the surface at about 50 to 70 kilometers up are the famous clouds. But these aren't fluffy water clouds like on Earth. They're made of sulfuric acid, concentrated sulfuric acid, the kind that would eat through your skin if you touched it, the kind that, if you got a drop of it on a piece of paper, would make the paper vanish in a puff of black smoke. And here's an obscure fact that most people don't know. Those clouds are so dense and reflective that Venus is actually the brightest object in the night sky after the moon. Not because it's producing light, but because it's reflecting about 75% of the sunlight that hits it. That pearly white crescent I saw through my uncle's telescope, that was sulfuric acid. Beautiful, isn't it? The most gorgeous evening star, and it's really just an ocean of poison hanging in the sky. But I'm getting ahead of myself, because I still haven't told you the answer to the biggest question of all. Why is Venus like this? Why did Earth's twin sister become a hell world while we ended up with beaches and coffee shops and functioning ecosystems? Bear with me, because to answer this, we need to go back. Way, way back to when the solar system was young and both planets had a chance to become something magnificent. And what I'm about to tell you is a story that has serious, terrifying implications for the planet you're sitting on right now. 4.5 billion years ago, our solar system was a mess. Just a rotating disk of gas and dust and rocks smashing into each other. Out of that chaos, planets formed, including 2 rocky worlds that would eventually be named Earth and Venus. They formed close together, made of essentially the same stuff. Silicate rocks, iron cores, similar amounts of water locked into their minerals. For the first billion years or so, both planets probably looked kind of similar. Volcanic, ocean-covered, steamy, wrapped in thick atmospheres of carbon dioxide and water vapor. If you'd visited either one back then, they might have seemed almost interchangeable. Here's where it gets interesting. On Earth, something amazing happened. As the planet cooled, water vapor in the atmosphere condensed into rain. Torrential, world-shaping rain that fell for millions of years, filling the low places with oceans. And once those oceans existed, they did something magical. They started absorbing carbon dioxide out of the atmosphere. You see, CO2 dissolves into water. It reacts with dissolved minerals to form carbonates, which sink to the ocean floor and get buried. Over hundreds of millions of years, this process pulled almost all of Earth's original carbon dioxide out of the sky and locked it up in rocks. Limestone, chalk, marble. All those white cliffs and towering mountains of sedimentary rock are basically petrified atmosphere. Fun fact that always blows my mind. If you took all the carbon dioxide currently buried in Earth's rocks and released it back into the atmosphere, our air pressure and composition would look shockingly similar to Venus. We're not that different. We just have somewhere to put our carbon. But on Venus, this beautiful cycle never got started. Or if it did, it failed. And the reason why comes down to one crucial factor. Venus is just a little bit closer to the Sun, about 30% closer to be specific, which means Venus receives roughly twice as much solar energy per square meter as Earth does. That extra energy was catastrophic because at Venus's distance from the Sun, water vapor in the atmosphere doesn't easily condense into liquid oceans. It stays as gas. And water vapor, here's the crucial part, is itself a powerful greenhouse gas. So the more water evaporates, the hotter it gets. The hotter it gets, the more water evaporates. The more water evaporates, the hotter it gets. You see where this is going. Scientists call it a runaway greenhouse effect. It's a feedback loop with no natural break. And once it starts, it doesn't stop until every last drop of water on the planet has been boiled into the sky. And then, over billions of years, ultraviolet radiation from the sun breaks apart those water molecules into hydrogen and oxygen. The hydrogen, being very light, escapes into space. The oxygen bonds with other elements. And just like that, all the water is gone. Forever. That's what happened to Venus. It cooked itself. It boiled its oceans away. It lost its water to space, one molecule at a time, over a period of about 1 billion years. And with no water, there was nothing to pull the carbon dioxide out of the atmosphere. So the CO2 just kept building up and building up and building up until the sky became so thick and heavy that heat could no longer escape. And that, my friends, is why Venus is hell. It's not just close to the sun. Mercury is closer, and Mercury isn't nearly as hot. Venus is hell because it has an atmosphere that traps almost 100% of the heat that hits it. It's a greenhouse effect turned up to 11. It's what happens when a planet's climate system completely, permanently breaks. Now, here's the part where I need to stop and be honest with you. Because scientists used to think Venus's fate was completely, totally impossible on Earth. We're too far from the sun. Our oceans are stable. Our carbon cycle works. We're safe. But recent research has shown that the situation is more complicated than we thought. And I'll get to that in a little bit. Because first, I need to tell you about the weirdest thing about Venus. The thing that doesn't fit any of our models. The thing that, honestly, might mean that everything I just told you is wrong. Let me set the scene. It's 2020. The world is falling apart because of the pandemic. Nobody's really paying attention to space news. And a small team of astronomers working with a radio telescope in Hawaii and another one in Chile quietly publish a paper. The paper is technical, boring looking, full of jargon, but the finding when you actually read it is stunning. They detected a chemical called phosphine in the clouds of Venus. Now, why does that matter? Phosphine is a molecule made of one phosphorus atom and 3 hydrogen atoms. On Earth, it's found in exactly 2 places. Deep in the atmospheres of gas, giants like Jupiter, where extreme heat and pressure can forge it through non-biological chemistry, and in the guts of certain anaerobic bacteria, microbes that live without oxygen, in swamps and sewage, and the intestines of animals. That's it. Those are the only known sources. Venus obviously is not a gas giant. It doesn't have Jupiter's crushing pressures deep inside a hydrogen atmosphere. So the fact that phosphine was showing up in the Venusian clouds in concentrations that shouldn't be possible from any known chemistry meant one of 2 things. Either there was some completely new chemical process happening on Venus that we didn't understand, or, and I want you to sit with this for a moment, there was something alive up there in the clouds making phosphine. The scientific community predictably lost its collective mind. Papers came out, papers were retracted. Other papers said the phosphine wasn't really there. More papers said it was, but maybe less of it than originally reported. As of now, in 2026, the debate is still going on. Some researchers stand firmly behind the detection. Others say it was an artifact of the data. The truth is, we don't know yet. But here's the thing. Here's what I find so fascinating about this whole story. The surface of Venus is definitely dead. Nothing could survive down there. But the clouds are different. At an altitude of about 50 kilometers above the surface, the temperature is a pleasant 30 to 70 degrees Celsius. The pressure is roughly the same as Earth's surface. It's actually, believe it or not, one of the most Earth-like environments in the entire solar system, aside from Earth itself. Sure, the clouds are made of sulfuric acid, but we know of extremophile microbes on Earth that thrive in acidic environments. There are bacteria that live in battery acid. There are microbes in volcanic hot springs, in nuclear reactor cooling pools, in the depths of the ocean where sunlight has never reached. So could there be life in the Venusian clouds? Floating microbes that live in droplets of acid, drifting on the wind, photosynthesizing off the sunlight that filters through from above? In my opinion, the answer is, we don't know. And that's exactly why we need to send more spacecraft to find out. And we are. NASA has a mission called Da Vinci, planned for launch in 2029, which will parachute a probe through the atmosphere and directly sample the clouds. There's another mission called Veritas that will map the surface in unprecedented detail. And the European Space Agency has a mission called Envision that will study the planet's atmosphere and geology together. Within the next decade, we're going to know, we might find that phosphine detection was just a chemical curiosity, or we might find that Earth's twin sister is home to the second known example of life in the universe. Either answer changes everything. But wait a sec. I want to pause here because I've been talking a lot about the big picture stuff, and I feel like I've been rushing past some of the truly bizarre details about Venus. Details that, when you first hear them, make you question whether the universe is just like actively trying to mess with our heads. Here's the deal. Venus rotates backwards. I know that sounds like a random fact people say to sound smart at parties, but let me actually explain what this means. Every other planet in the solar system rotates in the same direction that they orbit the sun. If you were floating above the North Pole of the solar system looking down, you'd see all the planets spinning counterclockwise. Earth spins counterclockwise. Mars spins counterclockwise. Even Uranus, which is tipped on its side, like it lost a fight with something big, technically rotates in the right direction. Venus, though, Venus goes the other way. It spins clockwise. If you were standing on the surface and you could see through the clouds and you weren't being crushed and burned to death, you would see the sun rise in the west and set in the east. Why? Nobody's really sure. The leading theory is that at some point in Venus's ancient history, something enormous crashed into it. Some Mars-sized planetary body wandering through the early solar system smacked into Venus with such force that it literally flipped the planet upside down or reversed its rotation. Imagine that. An impact so violent it changed which way a whole world was spinning. And we can still see the evidence today, 4.5 billion years later, in every sunrise that isn't happening. Oh, and it gets weirder. Venus rotates so slowly that a single day on Venus, meaning one full rotation, takes about 243 Earth days, but a year on Venus, meaning one full orbit around the Sun, only takes 225 Earth days. Read that again because I want it to sink in. A day on Venus is longer than a year on Venus, which means if you were somehow living on Venus, you would experience roughly 2 sunrises per year. And they would happen in the West, and they would be separated by 117 Earth days of continuous darkness, which sounds miserable, honestly, but also kind of poetic in a way. Here's another one that always trips me up. The winds. At the surface of Venus, the atmosphere is so thick that the wind moves incredibly slowly, like a lazy river of hot syrup. You'd feel like you were wading through molasses. But up in the clouds, at that 50 to 70 kilometer altitude I mentioned, the winds rip along at speeds of up to 400 kilometers per hour, and they blow in the same direction, all the way around the planet in just 4 Earth days. This is called super rotation. The atmosphere is spinning around the planet about 60 times faster than the planet itself is rotating. Nobody fully understands why. It's one of those things where you look at the data and you're like, that shouldn't be happening. And yet there it is, happening, and Venus doesn't care about your models. Perhaps my favorite obscure Venus fact, though, is this. On the surface, if you were somehow able to survive long enough to look up, the sky wouldn't be blue, or black, or even orange, really. The dominant color would be a kind of dim, sulfurous yellow-brown, and because of the thick atmosphere, light bends in weird ways. You'd be able to see over the horizon. The ground would curve up and away from you in every direction, like you were standing in the bottom of a shallow bowl. The Soviet Venera 13 lander, which touched down in 1982 and lasted a heroic 127 minutes before dying, sent back color photographs that showed exactly this. A yellow sky, brown-orange rocks, a horizon that seems to lift up around you like the walls of a curved room. There's this melancholy quality to those pictures that, I don't know, I find really beautiful. It's like looking at photographs from another lifetime, which, in a way, they are. Anyway, let me get back to the main thread, because I want to talk about something that keeps a lot of climate scientists up at night. And that's what Venus has to teach us about our own planet. Here's the point. For a long time, scientists were pretty confident that Earth couldn't experience a runaway greenhouse like Venus did. We're too far from the sun. Our oceans are too large. Our carbon cycle is too robust. Even if we burned all the fossil fuels on Earth, the standard climate models suggested we'd end up hot and miserable, but not, Venusified. But in 2013, a team of researchers led by Colin Goldblatt at the University of Victoria published a paper that quietly changed the conversation. They ran more sophisticated climate models than had ever been used before. And what they found was that the threshold for triggering a runaway greenhouse might be lower than we thought. Not by a lot, but by enough to matter. In their models, if the sun were just a bit brighter, or if we had a bit more greenhouse gas in the atmosphere, Earth could potentially cross a tipping point where the oceans would start evaporating faster than they could condense. And once you cross that line, there's no coming back. The feedback loop takes over. Water vapor traps more heat. More heat evaporates more water. And on until you have a Venusian sky and no more oceans and no more life. Now, I want to be really careful here because the science on this is nuanced. Most researchers still don't think that human-caused climate change, as bad as it is, could actually trigger a full runaway greenhouse on Earth. The more likely outcome from our current emissions trajectory is that we cook ourselves in more subtle, boring ways, mass extinction, ecosystem collapse, sea level rise, widespread famine, the standard apocalypse. But here's the thing that fascinates me: the sun is getting brighter. Not fast. On human timescales, it's basically imperceptible. But over the next billion years or so, the sun's luminosity will increase by about 10%. And at some point in that timeline, Earth will cross the threshold for a runaway greenhouse effect. Naturally, inevitably without any help from us. Estimates vary, but most models suggest that Earth has somewhere between 500 million and 1.5 billion years of habitability left. After that, we become Venus. The oceans boil, the atmosphere thickens, the temperature climbs, and this planet, this beautiful blue marble, becomes another hell world orbiting a slightly older, slightly angrier star. I find that thought deeply unsettling, but also, in a strange way, comforting, because it means Venus isn't just a random cosmic accident. It's a chapter in the natural life cycle of rocky planets. Everyone gets a turn. Earth had ours. Now it's Venus. And someday, Earth will join it. Unless, of course, we figure out how to leave, which is a whole other conversation. Let me tell you about a personal experience that shifted how I think about all this. A few years ago, I was traveling in the American Southwest, just driving through the desert with no real plan, and I ended up in the Mojave one evening, in this place where there's nothing around for maybe 50 miles in any direction. No towns, no lights, just cracked earth and mountains and this enormous, absurd sky. I pulled over at a random overlook and got out of the car. It was hot. Not Venus hot, obviously, but that dry, empty desert heat that makes your throat feel like paper. The wind was blowing. And when I looked up, Venus was hanging in the western sky, just after sunset. Brilliant white. Not twinkling, because planets don't twinkle like stars do. They just glow. And I remember thinking about how weird it was that I could stand there in this hostile landscape where you die of thirst in 3 days and look up at another planet where you die in 3 seconds. Two hells, one much less hellish than the other, connected by nothing but a line of sight and about 40 million kilometers of vacuum. I felt this weird kinship with Venus in that moment. Like, here's this planet that had the same start as we did. Same materials, same neighborhood, same rough age, and it just kind of drew the short straw. It ended up too close to the fire, and now it sits out there cooking forever. And we sit here in our little green oasis, taking turns pretending we're immortal. Anyway, sorry, getting philosophical. Let me get back to the actual science because there's so much more to talk about. Let's discuss the surface of Venus in more detail, because thanks to radar mapping from spacecraft like Magellan, which orbited Venus from 1990 to 1994, we actually have really detailed topographic maps of the entire planet, even though we've never seen it with our eyes. Radar can penetrate the clouds. Visible light can't. And what those radar maps revealed was unexpected. Venus is weirdly smooth. Not smooth like a billiard ball, but smooth compared to what we'd expect for a rocky planet of its size. There are mountains, sure. There's a massive highland region called Ishtar Terra, roughly the size of Australia, that contains the highest point on Venus, a mountain called Maxwell Montes. Maxwell rises about 11 kilometers above the mean surface level, which makes it taller than Mount Everest. There's another highland region called Aphrodite Terra, which is even bigger, about the size of South America, sprawling along the equator. But most of Venus, maybe 80% of it, is these vast rolling volcanic plains. Nothing like the rugged, tectonically twisted landscapes of Earth. And that's a huge clue about what Venus is up to on the inside. Here's the thing: Earth has plate tectonics. Our surface is made of these massive slabs of rock floating around on a partially molten mantle, colliding and grinding and sliding past each other. This is why we have earthquakes, why we have mountain ranges like the Himalayas, which formed when India smashed into Asia and just kind of kept going. It's why we have volcanoes clustered along specific lines. Plate tectonics is basically the engine that drives most of Earth's geological drama. Venus, though, doesn't have plate tectonics. As far as we can tell, Venus has one single solid crust. No plates, no collisions, no subduction zones where old crust gets recycled back into the mantle. So how does Venus release its internal heat? Because it has to, right? Every planet has a hot core, and that heat has to go somewhere. If it can't leak out through plate boundaries like it does on Earth, where does it go? Here's what the current theory suggests, and it's kind of terrifying. Venus releases its heat in massive planet-wide volcanic resurfacing events. Every few 100 million years or so, the entire planet basically melts. The whole crust turns molten. Volcanoes erupt everywhere at once. New lava floods across the entire surface, burying whatever was there before under fresh basalt. And then things cool down and reset until the heat builds up again. This is called the catastrophic resurfacing hypothesis. And we have some evidence to support it. When we count craters on Venus, they're weirdly evenly distributed. On the Moon or on Mars, you find some really old cratered regions and some younger, smoother regions, because different parts of those planets formed or reformed at different times. But on Venus, the craters seem to be spread out pretty uniformly, which suggests that the whole surface is roughly the same age, somewhere around 500 to 800 million years old, which means the entire surface of Venus, everything we see, formed in the geological blink of an eye, when the whole planet essentially remade itself in a fiery reset. Now, is Venus still volcanically active today? That's been an open question for decades. But in 2023, a team of scientists led by Robert Herrick at the University of Alaska went back through old Magellan radar data and found something incredible. They spotted a volcanic vent called Mont Mons that had visibly changed shape between two radar images taken just 8 months apart in 1991. The vent had grown larger, and there was fresh lava around it. This was the first direct evidence that Venus is still volcanically active today, not just in the distant past. Right now, as you're watching this video, there are probably volcanoes erupting on Venus. Rivers of lava flowing under those acid clouds. A whole planet alive with fire, and we're just now figuring it out. There's another obscure fact I want to throw in here because it's one of my favorites. Venus has these features called coronae, which are these huge, roughly circular structures on the surface, ranging from about 100 to 2,600 kilometers across. There are hundreds of them, and nobody's exactly sure what they are. The leading theory is that they're the surface expressions of hot upwelling plumes of magma from deep in the mantle, which push up on the crust and then collapse back down, leaving these ring-shaped scars. They don't really exist anywhere else in the solar system. They're a uniquely Venusian phenomenon, and they hint at a completely different style of geology than what we're used to on Earth. It's like Venus decided to reinvent how a planet works, and it did it in the most alien way possible. Kind of makes me wonder how much we're missing when we assume Earth is the template for how rocky planets should behave. Because Venus, right next door, is doing everything differently. Let me take another detour here because I want to talk about the atmosphere of Venus in a bit more detail. Because it's so much more than just, a lot of carbon dioxide. The Venusian atmosphere is structured in layers, kind of like Earth's, but way more extreme. Down at the surface, you have this dense, hot, slow-moving soup of gas that behaves almost like a fluid. Above that, you get the main cloud deck, which stretches from about 45 to 70 kilometers up. And within that cloud deck, there are actually 3 distinct layers of clouds made of different mixtures of sulfuric acid droplets of different sizes. Some scientists have compared it to a layer cake of poison. Above the clouds, you have a haze layer, and then above that, the atmosphere gets thinner and thinner until you reach the ionosphere, where the sun's radiation ionizes the gases into a soup of charged particles. Here's something that blew my mind when I first learned it. The upper atmosphere of Venus, at around 100 kilometers altitude, has a bizarre asymmetry. The day side is hot and stable, obviously, because the sun is beating down on it. But the night side, weirdly, is completely different. It's cold, sometimes dipping to minus 175 degrees Celsius. And it's dynamic, full of these strange oscillations and waves that scientists are still trying to figure out. On Earth, the day side and night side of the atmosphere aren't that different because our planet rotates once every 24 hours, and we have oceans that regulate temperature. But Venus rotates so slowly and has no oceans, so the two hemispheres are basically two completely different worlds sitting side by side. There's a permanent, invisible line running around Venus where the atmosphere transitions from one regime to another, and understanding that transition zone is one of the big open questions in planetary science. For instance, one of the strangest features of Venus's atmosphere is something called the polar vortices. At each of Venus's poles, there's a massive, permanent double hurricane, not a normal hurricane with one eye, but two eyes. Two swirling centers of rotation, dancing around each other in this hypnotic, ever-changing pattern. They form a kind of figure-8 shape from above. Nobody knows exactly why this happens. It's another one of those Venusian mysteries that doesn't fit our terrestrial intuitions. When the European Space Agency's Venus Express spacecraft observed these vortices in detail from 2006 to 2014, the scientists were basically like, this shouldn't work like this. And yet, here it is. By the way, Venus Express is worth pausing on for a second, because it did some incredible science that most people have never heard of. It confirmed the presence of lightning in the Venusian atmosphere. Actual, honest-to-God lightning flashing through those acid clouds. Which is weird because on Earth, lightning is usually associated with water clouds and ice crystals, not sulfuric acid. But something in the Venusian atmospheric chemistry is generating enough electrical charge separation to produce lightning strikes. Imagine standing on the surface of Venus and looking up. You'd see this dim, yellow-brown sky, hot enough to melt lead, and occasionally, arcing across those poisonous clouds, would be flashes of electric fire. Reality is so much stranger than fiction, isn't it? Sometimes I forget that Venus is a real place. It sounds like something from a fever dream. Okay, so I've told you about the atmosphere, the surface, the geology, the possible life, and the runaway greenhouse effect. Now let me tell you about the really speculative, cutting-edge stuff, the ideas that are just barely on the edge of respectable science. because this is where things get really wild. Here's a question that's been circulating in planetary science circles for a while now. Was Venus ever habitable? Not now, obviously. Now, Venus would kill you in seconds. But in the distant past, was there a time when Venus had liquid water on its surface, oceans, rivers, a breathable atmosphere? The evidence is tantalizing. In 2016, a team of researchers at NASA's Goddard Institute for Space Studies ran a series of climate simulations of ancient Venus. They wanted to see if the planet could have had a stable climate with liquid water for a significant chunk of its early history. What they found was surprising. Their models suggested that Venus might have had liquid water oceans and a moderate, Earth-like climate for up to 2 or 3 billion years, not just a brief window in the distant past, billions of years, which is longer than complex life has existed on Earth. Let that sink in. If those models are correct, Venus was potentially habitable for a longer stretch of its history than Earth has been home to multicellular organisms. And then, at some point, probably around 700 million years ago, something tipped the balance. The runaway greenhouse effect kicked in. The oceans boiled, the atmosphere thickened, and Venus, in a relatively short geological period, transformed from a possibly life-bearing world into the hellscape we see today. Which raises this deeply uncomfortable question. If Venus was habitable for that long, did it develop life? And if it did, what happened to that life? Because here's the thing. If Venus had oceans and moderate temperatures for billions of years, and if the same basic chemistry that produced life on Earth was operating on Venus, then it's not crazy to suggest that Venus might have had its own biosphere. Microbes at minimum, maybe more. And when the greenhouse effect boiled the oceans, that life would have faced a slow apocalypse. Some of it might have retreated into the crust, into hot rocks where it could survive. Some of it, kind of like I mentioned earlier, might have adapted to living in the clouds, drifting through the sulfuric acid haze, using photosynthesis to eke out an existence in the last remaining habitable layer of the atmosphere. That's the current speculation behind the phosphine detection. It's not just that there might be alien microbes on Venus right now. It's that those microbes might be the last exhausted survivors of a Venusian biosphere that once thrived on the surface before the sky fell in on itself. I don't know about you, but I find that idea absolutely haunting. A whole biosphere dying over millions of years, retreating higher and higher into the atmosphere as the surface below turned to a furnace, and then maybe a lucky few strains of microbes floating in the clouds forever, watching their home planet cook itself alive. If that's true, and it's still a huge if, then Venus isn't just a warning about climate, it's a graveyard. And there might still be flowers growing in it. To recap where we are. We've talked about how Venus formed, how it went wrong, how it might have been habitable once, how it might still have life in its clouds, and how it presents an unsettling mirror for our own planet's future. Let me shift gears here and talk about something more practical, because if Venus is so hostile, why do we keep going back? What are the future missions to Venus actually looking for? And why should you care? The next big wave of Venus exploration is coming up fast. As I mentioned earlier, NASA's Da Vinci mission is scheduled to launch by the end of the decade. Da Vinci stands for Deep Atmosphere Venus, Investigation of Noble Gases, Chemistry, and Imaging, which is one of those tortured acronyms that NASA loves. What it will actually do is send a probe on a suicide dive through the Venusian atmosphere, sampling the air at various altitudes and taking high-resolution photographs of the surface on the way down. The probe will only survive for about an hour before being crushed, but in that hour, it will collect more direct atmospheric data than we've gathered in decades. It's specifically designed to look for chemical signatures of past oceans, to measure the exact ratios of different isotopes of hydrogen and oxygen, which can tell us how much water Venus used to have. Because water molecules with different isotopes escape into space at different rates, and by measuring what's left, you can basically reverse engineer the history of Venusian water. Veritas, which stands for Venus, Emissivity, Radioscience, INSAR, Topography, and Spectroscopy, will orbit Venus and map its surface with a level of detail that makes Magellan look like a kid's drawing. It'll be able to detect elevation changes as small as a few meters, which means it could potentially spot new lava flows in real time if any happen during the mission. And then there's ENVISION from the European Space Agency, which will do a comprehensive study combining atmospheric, surface, and subsurface data. Together, these three missions represent the first serious return to Venus in a generation. For all intents and purposes, we've been ignoring our nearest planetary neighbor for way too long, distracted by the shinier promises of Mars and the outer solar system. There's also a really interesting private effort worth mentioning. Rocket Lab, the New Zealand-American aerospace company, has been developing a small, privately funded Venus probe as part of what they call the Rocket Lab Venus Life Finder. The plan is to launch a small probe with a very specific goal: to sample the cloud layer and look directly for signs of life. It's a bare bones mission with basically one instrument, a laser-based spectrometer that can detect complex organic molecules. If it works, it might be the fastest, cheapest search for alien life ever attempted. Here's what I find fascinating about all this. For most of the last 30 years, when we talked about searching for life beyond Earth, we mostly talked about Mars and Europa, one of Jupiter's moons, and Enceladus, one of Saturn's moons. These were the golden children of astrobiology. Venus was kind of an afterthought. Too hot, too hostile, too obviously dead to be interesting, but that's changed. The phosphine detection, whatever it turns out to be, cracked open a whole new way of thinking about Venus. And now there's this genuine, urgent scientific push to answer the big question. Are we alone in our own solar system? Or is there still a chance, however slim, that life exists just next door, hidden in the clouds of the planet we've been calling hell? I want to tell you another personal story here, because this stuff really does affect me on a deep level, and I think it might affect you too, if you let it. When I was in university, I took an astronomy class that I mostly signed up for because it fit my schedule. I wasn't a science major. I was into other things, honestly. I was studying literature and philosophy, and I thought this class would just be an easy elective. But there was one lecture right in the middle of the semester that changed my life. The professor, she was this soft-spoken older woman with wild gray hair and thick glasses. And she spent an entire hour and a half talking about Venus, just Venus. She didn't use PowerPoint, she just talked and drew things on the whiteboard. She told us about the Venera missions, about the Soviet engineers who had to invent titanium pressure vessels from scratch to survive that atmosphere. She told us about how they built the cameras with special cooling systems that they knew would only last minutes. She told us about the moment when the first surface image came back and the room of scientists at Mission Control just sat there in silence, staring at that grainy picture of rocks on another world. And then she said something that I still think about all the time. She said, "We spent decades imagining Venus as paradise. And when we finally got there, it turned out to be hell. Not because Venus was hiding something evil from us, but because our imagination was kind of projecting our own hopes onto a planet that never asked for them." Venus was just being Venus. It was our expectations that were wrong. And I remember walking out of that lecture and it was raining, one of those cold spring rains that soaks through your jacket. And I felt like I was seeing everything for the first time. Because that's kind of a lesson about everything, right? About science, about people, about how we go through life projecting our hopes onto things and then getting disappointed when reality turns out to be its own weird, wonderful, terrible thing. Venus doesn't owe us anything. It doesn't owe us habitability. It doesn't owe us life. It doesn't even owe us mystery. It just is what it is. And our job, as curious little bipeds on a nearby rock, is to try to understand it on its own terms. Anyway, that was, I don't know, kind of a rambling tangent. Let me get back to the science. I want to talk about magnetism because this is another huge difference between Venus and Earth, and it has real implications for habitability. Earth has a strong magnetic field. It's generated by the churning of molten iron in our outer core, which creates this invisible protective shield that extends thousands of kilometers into space. This magnetic field, called the magnetosphere, deflects most of the solar wind. That's the constant stream of charged particles blasting out from the sun. Without our magnetosphere, the solar wind would slowly strip away our atmosphere, molecule by molecule, over millions of years. Venus doesn't have a magnetic field. Or more precisely, it has an extremely weak one, less than 1/10,000th the strength of Earth's. This is another mystery. Because Venus is roughly the same size as Earth, has roughly the same composition, and presumably has a similar iron core. So why doesn't Venus's core generate a magnetic field like ours does? The leading theory is that Venus rotates too slowly. To generate a magnetic field through the dynamo effect, you need a molten metal core that's not just moving, but moving in specific complex patterns that require rotation. Earth spins fast, which helps churn our core in the right way. Venus, spinning once every 243 days, might just be too sluggish to sustain a magnetic dynamo. Another theory suggests that Venus's core has completely solidified. Once a core solidifies, the convection stops and the magnetic field dies. But we don't have direct evidence for this yet. It's another one of those questions that future missions might help answer. Now here's why the lack of a magnetic field matters. Without a magnetosphere to protect it, Venus's atmosphere is directly exposed to the solar wind. And over the past 4 billion years or so, that solar wind has been slowly, relentlessly stripping Venus of its lighter atmospheric components, especially hydrogen, which used to be part of water molecules, which is one of the reasons Venus lost its oceans and can't ever get them back. It's a brutal cascade. No fast rotation, no magnetic field. No magnetic field, no protection from the solar wind. No protection from the solar wind, no water. No water, no way to sequester carbon dioxide. No way to sequester CO2, runaway greenhouse. Runaway greenhouse, hell world. Every step of that chain on Earth went the other way. We rotate fast. We have a magnetic field. We keep our water. We sequester our carbon. Our climate stays moderate. We get to have puppies and pizza and jazz. The margins between livable and lethal are so thin. It's almost embarrassing how much of our existence depends on happy coincidences we barely understand. Let me tell you an obscure thing that I find utterly fascinating. Venus has these features on the surface called pancake domes. They're these huge, flat-topped, roughly circular volcanic structures that look like, well, giant pancakes. They can be up to 65 kilometers across and about a kilometer tall. and they don't really form anywhere else in the solar system. On Earth, when volcanic magma erupts, it either spreads out into thin sheets or piles up into steep cones, depending on how thick and sticky the lava is. But on Venus, the extreme atmospheric pressure and heat cause the lava to behave differently. It kind of oozes out slowly and then just sits there, piles up into these squat symmetrical mounds. Some of them have concentric ridges around them, like the ripples in a bowl of pudding after you've dropped a spoon in. There are hundreds of these pancake domes across Venus. And they're just one of the many weird alien geological features that make Venus feel like an actual distinct place with its own personality. Not a failed Earth, not a warning about what could go wrong, just kind of its own thing, doing its own thing, making its own weird lava pancakes. I love that about Venus. It's not just a cautionary tale. It's a whole world with its own history and its own beauty. And once you look past the horror of its climate, there's a strange, mesmerizing loveliness to it. Here's another obscure fact for you. If you were somehow able to survive on the surface of Venus and you jumped, you'd fall back down at about the same rate you would on Earth. Because Venus has almost identical gravity to Earth. It's about 90% as strong, which means in terms of how your body would feel in the gravitational sense, standing on Venus would be pretty much indistinguishable from standing on Earth. Everything else about the experience would kill you instantly, but at least your bones wouldn't feel weird about it. There's a proposal that comes up periodically in space exploration circles that I want to mention because it's one of the most beautifully strange ideas in modern astronautics. It's called the HAVOC concept, which stands for High Altitude Venus Operational Concept. NASA researchers have been kicking this idea around for years. The idea is this: the surface of Venus is uninhabitable, but at about 50 kilometers altitude, the atmosphere is, as I mentioned, one of the most Earth-like environments in the solar system. Room temperature, Earth normal pressure, gravity almost identical to what we're used to. There's just the small matter of the sulfuric acid clouds. But here's the wild part. Earth's normal air, our breathing mixture of nitrogen and oxygen, is actually a lifting gas on Venus. Because Venus's atmosphere is so dense, being made of heavy carbon dioxide, that regular Earth air is lighter than it, which means a big enough balloon or airship filled with just plain old breathable air would float in the Venusian atmosphere. You wouldn't need helium or hydrogen, you just need the same stuff you're breathing right now. So the HAVOC proposal imagines cities floating in the Venusian clouds. Enormous airships filled with regular air, hosting crews of scientists and explorers, drifting at that 50-kilometer altitude where the temperature is nice and the pressure is comfortable. They'd have to be built out of materials that resist sulfuric acid, but that's a solvable engineering problem. Coated in Teflon or specialized polymers, these floating habitats could theoretically last for years. And the view. Imagine that view. You'd be gliding through amber-colored clouds, illuminated by the diffuse light of a sun you can't quite see. Beneath you, the crushing hell of the surface, hidden by the cloud deck. Above you, if you climbed high enough, you might see stars through the haze. You'd be a citizen of the sky, living in the atmosphere of a planet that could otherwise never host you. It sounds like science fiction, and honestly, we're probably nowhere near actually doing this. But the fact that it's physically possible, that the math works out, is one of those things that reminds me how weird and wonderful the universe is. Ultimately, Venus keeps surprising us. Every time we think we've figured it out, some new detail emerges that reshuffles the whole picture. That's what I love about science. It's not a static body of facts. It's an ongoing conversation with the universe, and Venus is one of the loudest voices in the room. Let me step back and think philosophically for a moment, because I've been throwing a lot of information at you, and I want to take a beat to reflect on what all of this means. Venus is, in many ways, a mirror. When we look at Venus, we see what Earth could have been, or what Earth could still become, or what Earth will inevitably become on cosmic timescales. Venus is the road not taken, and also the road that leads to where we're all going eventually. There's something humbling about that, something that makes you look at the sky differently. When I see Venus glowing in the evening now, after all these years of learning about it, I don't just see a bright star. I see a warning, and a memorial, and a possibility, and a piece of the same story that includes my own existence. Because the same processes that made Venus hell almost certainly happen elsewhere in the galaxy. There are probably billions of Venus-like planets scattered across the Milky Way, rocky worlds that started with promise and cooked themselves alive. Each one, potentially, hosting a story that will never be told. Each one, potentially, a graveyard for life that briefly flickered and then was extinguished by physics. And Earth is one of the lucky ones. We're one of the outliers. We're the planet where things went right, at least so far. And that luck, that impossibly narrow window of habitability, is what we're now busy screwing up with our own reckless carbon emissions. I don't want to turn this into a lecture about climate change, but I also can't talk about Venus without acknowledging that we're currently running a very expensive, very risky experiment on our own atmosphere. And Venus is sitting right there in the sky, showing us what happens when planetary climate systems fail catastrophically. It's like the universe has provided us with a real-time visual aid, and we're mostly just kind of ignoring it. Here's the deal. I think Venus deserves more attention than it gets, not because it's dangerous, or because it might have life, or because it's a warning about our future, although those are all true, but because it's fundamentally weird, because it's a whole other world with its own history and geology and atmosphere, and we've barely started to understand it, because it's the closest planet to us, and we've been mostly ignoring it for decades. If aliens landed tomorrow and asked us what we know about our nearest planetary neighbor, we'd have to sheepishly admit that most of our best data comes from spacecraft designed and launched during the Cold War. That's kind of embarrassing, right? Like, we've got fancy rovers on Mars, we've flown past Pluto, we've orbited Jupiter and Saturn, we're on our way to Uranus and Neptune. But Venus, our sister planet, the bright star in the evening sky that everyone on Earth has been looking at for as long as there have been humans, we know less about the surface of Venus than we know about the surface of Mars, which is wild, because Venus is closer and easier to reach. Anyway, sorry, I'm ranting. Let me pull it back together and start wrapping this up, because we've covered a lot of ground and I want to make sure we land somewhere meaningful. Let me tell you about one more mystery that I haven't touched on yet. This one might be my favorite because it's so simple and yet so completely unresolved. There's a strange feature in the Venusian atmosphere called the unknown UV absorber. When you look at Venus in ultraviolet light, you don't see a uniform, smooth cloud deck. You see these weird, dark streaks and patches. Something in the upper atmosphere of Venus is absorbing ultraviolet light. A lot of it. About half of the total solar energy that Venus receives gets absorbed in the ultraviolet range by whatever this substance is. And we don't know what it is. We've known about the UV absorber since the 1970s. Every spacecraft that's flown by Venus has confirmed it. But despite half a century of study, nobody has definitively identified what molecule or compound is doing the absorbing. There are theories, sulfur compounds of various kinds, iron chloride, complex organic molecules, but none of them quite match the observations. Some scientists have suggested, and this is speculative but fun, that the UV absorber might be biological, that the pattern of dark patches in the atmosphere might correspond to concentrations of microbes floating in the clouds, absorbing UV as a byproduct of their metabolism. This is a minority view, and most researchers assume the explanation is some kind of exotic chemistry. But the fact that we've been staring at Venus for decades and still can't figure out what's coloring its clouds is a pretty stark reminder of how much we don't know. Every planet keeps secrets. Venus, being wrapped in permanent cloud cover, keeps more than most. There's another obscure fact I want to sneak in before we close. Venus has no moons. Neither does Mercury. But all the other planets in the solar system have moons. Some of them lots and lots of moons. Jupiter has 95 confirmed satellites at last count. Saturn has 146. Even Mars has its two little potato-shaped moons, Phobos and Deimos. Venus, though, is alone, just spinning slowly, backwards, in the dark, with no companion. Which is another one of those weird facts that makes you wonder about Venus's history. Some scientists have proposed that Venus might have had a moon in the distant past, one that was lost during whatever catastrophic event flipped the planet's rotation. Maybe that giant impact that reversed its spin also destroyed or ejected its moon. We'll probably never know. But it's a lonely image, isn't it? A whole planet, orphaned in its own orbit, with no moon to keep it company through the endless slow days. You know, when I think about Venus, I sometimes imagine what it must have looked like billions of years ago, if the habitability models are right. Before the atmosphere thickened, before the oceans boiled, when there was still liquid water on the surface and the clouds above were water vapor, not sulfuric acid. Picture that world. Blue oceans, white clouds, a sky that was probably bluish or maybe pinkish, depending on the atmospheric composition at the time. Continents of raw volcanic rock rising out of the seas. Maybe, just maybe, microbial mats growing in the shallow waters. A whole planet, humming with the same kind of geological and possibly biological activity that was happening on Earth at the exact same time. Two twin planets, two blue worlds. And then, slowly, one of them started to change. The temperature crept up. The oceans began to evaporate faster than they could rain back down. Ice caps at the poles, if there were any, melted. The atmosphere thickened, and over a period that was long on human scales but short on cosmic scales, that beautiful blue world became the yellow-brown furnace we know today. If there was life on early Venus, it either died out slowly or it fled upward into the clouds and is maybe still there, waiting for us to notice it. Either way, it's one of the most tragic and profound stories in our cosmic neighborhood. A planet that had everything and lost it, because it was just a little too close to the fire. Maybe there's a lesson in there, or maybe there isn't. Maybe planets, like people, just get dealt different hands, and there's no cosmic justice determining who ends up in paradise and who ends up in hell. Venus didn't deserve its fate any more than Earth deserves ours. It's just physics playing out on a stage so vast and slow that we can barely comprehend it. But here's what I keep coming back to. We can comprehend it. That's the miracle, that we, these tiny, brief, absurd creatures on a small rocky planet, have looked up at that bright light in the evening sky and, over the course of a few thousand years, figured out that it's another world, figured out what it's made of, figured out how it formed, figured out why it's the way it is, figured out how it might have once been habitable and why it isn't anymore. That's kind of astonishing when you really think about it. Every fact I've shared with you in this video was earned. Someone worked to figure it out. Someone stayed up late doing calculations. Someone built a spacecraft that traveled 40 million kilometers to a hostile planet and sent back data before being destroyed. Someone squinted at that data through blurry graphs and thought, hey, this looks weird, and pulled on that thread until they understood something new. That's how science works. That's how we know anything about Venus at all. And there's so much more to learn. Every new mission peels back another layer. The Da Vinci probe, when it drops through the atmosphere in the 2030s, will send back data that will probably rewrite half of what I've told you today. That's kind of the beauty of it. The story isn't finished. It's just paused, waiting for the next chapter. Okay? I want to leave you with something. A thought experiment. Tonight or on the next clear evening, wherever you are, go outside just after sunset. Or, if it's the wrong time of year for that, go out just before sunrise. Look toward the horizon where the sun is setting or about to rise. If Venus is currently visible from your location, you'll see it. You can't miss it. It's the brightest thing in the sky besides the moon. A steady, unblinking white light hanging there like a hole punched through the fabric of the twilight. That's a planet. That's another world. That's a place where lava flows under acid clouds, where the wind spins around the poles in double vortices, where the sky is yellow and the ground is hot enough to melt lead. That's a place where maybe alien microbes drift in droplets of sulfuric acid, the last survivors of a lost biosphere. That's a place we've barely visited and where we've never left a footprint. And it's right there, in the sky, where you can see it with your own eyes right now. Isn't that wild? Isn't that just kind of ridiculous? That we live in a universe where you can just look up and see another planet, a whole world spinning through the vacuum, catching the light of the same sun that's setting behind you. And it's been doing that for 4.5 billion years, longer than any human civilization, longer than any species that ever walked on Earth. And it'll keep doing it long after we're gone, long after Earth itself has gone the way of Venus, cooked into its own version of hell by a sun that keeps getting brighter. That's the story of Venus. It's a story about impermanence, about luck, about how thin the line is between paradise and hell, about how much can go wrong and how much can go right, and how the same universe that made Earth also made Venus, and there's nothing personal about it. It's just physics. But it's also our story, because Venus is us in another timeline, and we might be Venus in some future timeline. And in between, there's this beautiful, fragile, absurd moment when both planets exist at once, orbiting the same star, keeping each other company across the void. The next time you see Venus in the sky, wave. It's your sister planet. It's had a rough time. It's not doing so well, but it's still there. Still shining. Still holding on to whatever secrets it has left. And someday, someone is going to figure those secrets out. Maybe it'll be you. Maybe it'll be your kid. Maybe it'll be a spacecraft that hasn't been designed yet, launching in a year that hasn't happened yet, on a mission dreamed up by someone who hasn't been born yet. But someone will, and when they do, they'll wave back. I mentioned the Venera program earlier. Briefly, in passing, like it was a footnote. But honestly, the Soviet exploration of Venus is one of the most extraordinary engineering achievements in human history, and it deserves way more than a footnote. So let me tell you the whole story, or at least the parts that I find most incredible. The Venera program ran from 1961 to 1984. That's 23 years of continuous effort, 16 spacecraft, multiple failures, multiple successes, and a slowly accumulating body of knowledge about Venus that, for a while, made the Soviet Union the undisputed world leader in planetary exploration. Here's the context. In the early 1960s, both the United States and the Soviet Union were racing to be the first to send a spacecraft to another planet. Mars was harder to reach because it's farther away and takes longer to get to. Venus was the low-hanging fruit. It's closer and the launch windows come around more often. Both sides went for it. The Soviets got there first. Venera 1, launched in February 1961, was the first spacecraft ever aimed at another planet. It didn't work exactly. Communications were lost about a week into the flight, and the spacecraft flew silently past Venus without sending back any data. But it got there. It made the trip. It proved that interplanetary flight was possible. And then over the next 20 years, the Soviets kept trying. They kept building. They kept failing. And they kept learning from each failure. Venera 2 flew past Venus in 1966, but also went silent before it could return data. Venera 3 crashed into Venus that same year, making it the first human-made object to reach the surface of another planet, but its instruments had failed before impact, so we didn't get anything from it. Just a spacecraft-shaped dent somewhere on the Venusian surface. A tiny, unnoticed monument to Soviet ambition. Venera 4 in 1967 was the breakthrough. It successfully deployed a probe into the Venusian atmosphere, and for the first time in history, we got direct measurements of another planet's air. The probe transmitted data for about 93 minutes as it descended. It measured temperature, pressure, and composition. And what it found was deeply unsettling. Before Venera 4, most scientists still assumed Venus was, if not habitable, at least not crazy hostile. There were serious papers being written, speculating that the surface temperature might be around 100 degrees Celsius. Hot, sure, but not apocalyptic. Venera 4 measured pressures and temperatures that suggested it was way worse than that. But even Venera 4 didn't quite tell the whole story, because the probe stopped transmitting before it reached the surface. It got crushed by the atmosphere on the way down, which nobody had expected. The engineers had built it to withstand pressures they thought were realistic, and reality laughed at them. So they built Venera 5 and Venera 6 with stronger pressure hulls. Both were launched in 1969. Both descended into the atmosphere. Both got crushed before reaching the surface, because Venus's atmosphere was still worse than the new estimates. Venera 7, launched in 1970, was designed with the assumption that the surface pressure might be as high as 180 atmospheres, which sounded absurd at the time, but the engineers said, look, we've been wrong every time, let's overshoot. So they built a titanium pressure vessel designed to survive conditions that seemed almost cartoonishly extreme. And on December 15, 1970, Venera 7 became the first spacecraft in human history to successfully land on another planet and transmit data from the surface. I want you to really appreciate what that means. Because we talk about the moon landing all the time. Neil Armstrong, one small step, all of that. And it's amazing. Truly. But we also sent people to the moon It was a manned mission. There were astronauts. They came home. Venera 7 was a machine, built in secret in a country that was falling apart around itself, launched on top of a rocket that had a mixed track record, sent on a months-long trip to a planet nobody had ever landed on, and it survived. It touched down on the surface of Venus in an environment that would kill an unprotected human faster than you could scream, and it sent back a signal. The signal was weak, and initially the engineers thought the mission had failed. It took them weeks of analyzing the tapes to realize that Venera 7 had, in fact, transmitted data from the surface for about 23 minutes. 23 minutes of direct measurements from the surface of Venus. The first data ever collected from the ground of another world. And what it measured was pressure of about 90 atmospheres, temperature of 475 degrees Celsius, confirming definitively that Venus was hell. I sometimes think about the engineers who worked on Venera 7, what their lives were like, what their offices looked like, whether they had children who they had to keep secrets from because the Soviet space program was classified, whether they went home after that successful landing and told their spouses, "We did it, we landed on Venus," and whether their spouses even understood what that meant. Because I'm not sure the world understood what it meant. It happened during the height of the Cold War, buried under 100 other news stories, and it never quite got the recognition it deserved. There's a photograph, I've seen it a few times, of the Venera control room around this time. It's grainy black and white. Rows of engineers in white lab coats sitting at consoles with those big analog dials. The consoles look like something out of a 1960s sci-fi movie. And these people, these ordinary-looking Soviet scientists, they landed a spacecraft on another planet with slide rules and vacuum tubes. Because computers were still barely a thing, they did the math by hand. They built the hardware in workshops. And it worked. Anyway, the Venera program kept going after that first landing, and it just kept getting more ambitious. Venera 8 in 1972 landed and lasted 50 minutes. It measured light levels for the first time, and the scientists discovered that despite the thick cloud cover, quite a bit of sunlight makes it to the surface. Not as much as on Earth, but enough that if you were there, you'd be able to see, in an eerie, dim, yellow-orange kind of way. Venera 9 in 1975 sent back the first photograph ever taken from the surface of another planet. And I want you to sit with that for a second, because we're so used to seeing surface photographs from Mars now. There are literal panoramas from Mars that you can scroll around on your phone. It's easy to forget that at one point in human history, we had never seen the surface of any other world with our own eyes. The Venera 9 image is grainy. It's black and white. Its field of view is limited, but it's clearly a photograph of a real landscape. There are rocks in the foreground. Angular, flat-sided rocks like broken plates. The ground is covered in what looks like fine dust or gravel. The horizon curves upward in that weird way I mentioned earlier, a consequence of the thick atmosphere bending light. And in the distance, you can see more rocks. It's not much, but it's the first look anyone had ever gotten at the surface of another planet. Venera 10 later that same year sent back another surface photograph from a different location, and the landscape was strikingly different, more weathered, more dust-covered, which told scientists that Venus's surface wasn't uniform. There were different terrains, different geological histories in different places. Venera 11 and 12 in 1978 both landed successfully and made more atmospheric measurements. Venera 12 detected what scientists initially interpreted as thunder, suggesting the presence of lightning storms in the Venusian atmosphere, though this was controversial at the time and took decades to fully confirm. And then came the crown jewels. Venera 13 and Venera 14 launched in 1981, landing on Venus in March 1982. These two spacecraft are, in my opinion, the pinnacle of the entire Venera program. They were the most sophisticated, best equipped probes yet. And they returned the first color photographs from the surface of Venus. I want to describe these photographs to you because they're some of my favorite images in the history of space exploration, and they don't get shown nearly enough. The Venera 13 landing site was a rocky plain, covered in flat slab-like rocks that geologists later interpreted as volcanic basalt fragments. The sky above was a hazy orange-yellow, the color of a smoggy sunset that never ends. The ground itself was various shades of brown and ochre and rust, not because Venus is actually those colors under white light, but because the thick atmosphere filters out most of the blue wavelengths, so everything looks warm-toned, kind of like looking at the world through a piece of amber. The Venera 14 landing site was different again. Fewer rocks, more of a smooth plate-like surface, possibly volcanic bedrock that hadn't been broken up as much. And there's this one detail that always gets me. In the Venera 14 image, you can see part of the spacecraft itself in the foreground. There's a lens cap that had ejected during the landing sequence. And in the photograph, you can see that the lens cap landed exactly where the soil sampling arm was supposed to reach, which means the soil sampling arm scooped up the lens cap instead of the Venusian soil. The engineers back on Earth watching this on their monitors must have felt their souls leave their bodies for a second. All that effort, all those years of work to send a spacecraft to another planet, and it accidentally sampled its own lens cap, but they still got useful data because Venera 14 had multiple experiments and most of them worked fine. It was just that one specific experiment that got sabotaged by a piece of the spacecraft itself. And there's something so human about that, so relatable. You do everything right, you plan for every contingency, and then a lens cap falls in exactly the wrong spot, and you have to just kind of laugh about it and move on. The Venera 13 and 14 landers survived for 127 minutes and 57 minutes respectively, which is remarkable considering they were sitting in an environment that should have destroyed them almost instantly. They transmitted continuously until their electronics finally gave out from the heat. And then, just when you thought the Soviet Venus program couldn't get any more impressive, they went and did the Vega missions. Vega 1 and Vega 2, launched in 1984, were actually two-part missions. Because in addition to Venus, they were also going to visit Halley's Comet, which was making one of its rare passes through the inner solar system. So the Soviets designed spacecraft that could drop off Venus probes on the way to intercepting the comet, multitasking at an interplanetary level. The Venus probes from the Vega missions did something no other Venus lander had done. They deployed atmospheric balloons. Let me repeat that because it's easy to gloss over. They put balloons in the atmosphere of Venus. In 1985, actual functional balloons that floated in the Venusian clouds and transmitted data as they drifted. The balloons were about 3.5 meters in diameter when inflated. They were filled with helium. They floated at an altitude of about 54 kilometers, right in the middle of the main cloud deck, where the temperature and pressure are relatively benign. And they carried little instrument packages that measured wind speed, temperature, pressure, and cloud composition. The Vega balloons were only designed to operate for about 2 Earth days before their batteries ran out. But in those 2 days, They drifted about 11,000 kilometers across the face of Venus, riding the powerful high-altitude winds. And they gave us the first direct measurements of what the Venusian atmosphere is doing at cloud level. Nothing else has ever been done quite like this. We've had probes drop through atmospheres. We've had landers on surfaces. We've had orbiters looking down from above. But actual balloons floating in the sky of another world, sending back data as they drift. That was a uniquely Soviet achievement, and nobody has replicated it in the 40 years since. It's kind of criminal, honestly. Balloons on Venus are such a good idea, and we have the technology to do it much better now, but we just haven't. The Havalk concept I mentioned earlier, the floating cities idea, kind of grew out of the legacy of the Vega balloons, but we haven't sent so much as a scientific balloon back to Venus in 4 decades. The Vega balloons were the last of the great Venera era missions. After that, the Soviet Union collapsed, funding dried up, and the whole apparatus that had been sending spacecraft to Venus year after year just stopped. Kind of like an empire dying and taking its cathedrals with it. All that expertise, all those engineers dispersed. Some emigrated, some retired, some kept working, but on smaller, less ambitious projects. And Venus went quiet. There's this melancholy that hangs over Venus exploration, I think, because for a while we were doing so much. We were reaching for it constantly, and then we stopped. And Venus has been mostly waiting, alone, ever since. Occasional visitors, sure, a few flybys, Venus Express, Akatsuki, the Japanese orbiter, but nothing like the sustained, aggressive exploration of the 1960s through the 1980s. I think about that a lot, about how exploration is not a steady process. It comes in waves, it ebbs, it flows. It depends on politics and funding and public interests, none of which have anything to do with the actual scientific value of the target. Venus deserved better. It still does. And I hope the current wave of missions, the Da Vinci and Veritas and Envision projects, marks the beginning of a new era of paying attention to our closest planetary neighbor. Okay, let me shift gears for a bit, because I want to talk about something completely different now. Not the science of Venus, not the exploration of Venus, but the idea of Venus, the way Venus has lived in the human imagination for thousands of years, long before we had any way to actually see what it was really like. Venus has been visible in the sky for as long as there have been humans to look up. It's the brightest object in the sky after the sun and the moon. You can literally see it during the day if you know where to look. It's so bright that it sometimes casts shadows on Earth on very dark nights. It's impossible to miss, which means every civilization, everywhere on Earth from the beginning of history to now, has had a relationship with Venus. The ancient Sumerians called it Inanna and identified it as the goddess of love, war, and fertility, which is a weirdly comprehensive portfolio for one deity. But Inanna was one of the most important gods in the Sumerian pantheon, and she was associated with Venus specifically because Venus is unique among the celestial objects. It's the brightest star-like thing in the sky. It changes position dramatically. It appears in the evening and disappears, then reappears in the morning. It has a personality. The Babylonians inherited this tradition and called the goddess Ishtar. Same basic idea. Love, war, fertility. Venus. And they made incredibly detailed astronomical observations of Venus's movements. There's this ancient Babylonian text called the Venus Tablet of Ammisaduqa, which dates from around 1600 BCE. And it records the risings and settings of Venus over a period of 21 years. The precision of the observations is astonishing. These people were doing serious astronomy, 3,500 years ago, using nothing but their eyes and clay tablets. The Egyptians thought Venus was two separate objects, one that appeared in the evening and one that appeared in the morning. They called the evening one Tiumutiri and the morning one Waiti. It took a while for astronomers to figure out that these were the same object appearing at different times, because Venus's orbital patterns make it look like two different stars. The Greeks made the same mistake initially. They called the morning star Phosphoros, which means light bringer, and they called the evening star Hesperos. Eventually, Pythagoras, or one of his students, figured out that they were the same object, but the two names stuck around for a long time. Even today, when we talk about the morning star and the evening star as if they're distinct things, we're kind of echoing that ancient confusion. The Romans called Venus, well, Venus, named after their goddess of love and beauty. And that's the name that stuck for us, which is kind of ironic because Venus is a hellscape and the name evokes beauty. But the Romans didn't know that. To them, it was just a beautiful, bright light in the sky. And beauty deserved a beautiful name. The Mayans were obsessed with Venus, like next level obsessed. They tracked Venus's movements with incredible precision. There's a whole section of the Dresden Codex, which is one of the surviving Mayan books, that's dedicated entirely to Venus. It contains detailed astronomical tables that predict Venus's position in the sky over a period of 104 years. The accuracy of these predictions is stunning. The Mayans knew that Venus has a synodic period of 584 days, which is the time it takes to return to the same position relative to the Sun as seen from Earth. And they knew that 5 Venus cycles equal almost exactly 8 Earth years, which is a coincidence that meant a lot to them cosmologically. The Mayans associated Venus with war. Specifically, they would time their military campaigns to correspond with Venus's appearances in the sky. When Venus rose as the morning star after being invisible for a while, that was considered a particularly auspicious moment for battle, which means that real wars with real casualties were fought based on the position of a planet. Human beings killed each other or didn't, depending on where Venus was. There's something profound about that. The idea that our ancestors let the movements of the heavens dictate the movements of their armies. It's easy to look back on that as superstition, and I guess technically it was. But it also represents a kind of deep engagement with the cosmos that we've mostly lost. When was the last time you made a life decision based on where Venus was in the sky? For me, never. But for the Mayans, this was routine. The Chinese, meanwhile, had their own name for Venus. They called it Taibai, which means Great White One. And they associated it with metal specifically in the traditional 5-element cosmology. Which is interesting because the surface of Venus, as we now know, is largely covered in volcanic basalt and probably has significant metal content. The Chinese astronomers weren't making that connection. Obviously, they were doing symbolic cosmology, not geochemistry, but there's a weird poetry in it. The Great White One, made of metal. Various indigenous American cultures had their own Venus mythologies. The Skidi Pawnee, for instance, believed that the morning star and the evening star were divine parents who created the first humans, and they conducted a sacred ceremony, historically, that involved sacrificing a young captive to the morning star at the time when Venus appeared brightly in the pre-dawn sky. This was practiced up until the early 1800s, I believe. So again, real human lives were affected by Venus in the most direct and terrible way. A planet dictating the ritual calendar of an entire people. In Aboriginal Australian traditions, Venus is called Barnum Burr, and she's associated with the Jangawul creation myth. She rises in the east and guides the ancestors across the sky. There are songs about her that have been passed down for generations, maybe for tens of thousands of years, which means people were singing songs about Venus long before anyone in Europe had written anything down. I love this stuff because it reminds me that Venus isn't just a modern scientific object, it's a shared thing. Every culture on Earth has a relationship with Venus. Every civilization in every era looked up and saw the same bright light in the sky and made meaning out of it. The meaning changed, but the light stayed the same. And then, in the early 1600s, everything changed, because Galileo pointed his telescope at Venus. I want to spend some time on this because it's genuinely one of the most important moments in the history of science, and it happened because of Venus. Galileo built his first telescope in 1609. It was, by modern standards, terrible. Kind of like looking through a paper towel tube with a magnifying glass at the end. But it was better than anything that had existed before, and Galileo pointed it at everything he could think of. The moon, Jupiter, the sun, and Venus. When he looked at Venus over the course of many months in 1610 and 1611, he noticed something extraordinary. Venus went through phases, just like the moon. Sometimes it appeared as a full disk, sometimes as a half disk, sometimes as a thin crescent, sometimes almost invisible. This might not sound like a big deal to you, but it was a huge deal, because in the geocentric model of the universe, the one that had been dominant for over 1,000 years, Venus wasn't supposed to be able to do that. In the geocentric model, put forward by Ptolemy in the 2nd century and endorsed by the Catholic Church, Earth was at the center of the universe, and everything else orbited around us. In this model, Venus was supposed to move around Earth in a way that kept it between Earth and the Sun at all times, which meant that if you looked at Venus with a good enough telescope, you would only ever see it as a crescent, because you'd only ever see the illuminated side from the side, kind of. But Galileo saw full phases, which meant Venus was sometimes on the far side of the Sun from Earth, which meant Venus was orbiting the Sun, not the Earth, which meant Ptolemy was wrong, which meant Copernicus was right, which meant the Earth wasn't the center of the universe, which meant everything that the Catholic Church had been teaching about cosmology for centuries was kind of incorrect. Galileo published these observations in 1613 in a work called Letters on Sunspots, and it caused, as you might imagine, an enormous stir, because this was direct, observational, empirical evidence that the heliocentric model was correct. It wasn't just theoretical anymore. It wasn't just Copernicus's clever calculations. It was Galileo with his telescope showing everybody that Venus had phases and therefore the sun had to be at the center. The church did not take this well. You know the rest of the story. Galileo was eventually tried by the Inquisition in 1633 and forced to recant his support for heliocentrism. He spent the last years of his life under house arrest. It took the Catholic Church until 1992 to officially acknowledge that they had been wrong to condemn him, which is quite a delayed apology. But here's what I want you to sit with. The single most important piece of evidence in the scientific revolution, the observation that finally definitively broke the geocentric model, was the phases of Venus. Not the moons of Jupiter, although those helped. Not the mountains on the moon, not the sunspots. The phases of Venus. That was the killing blow to the old cosmology, which means Venus, in a very real sense, is the planet that gave us modern science. If Venus had been positioned differently, or if it hadn't gone through observable phases, the heliocentric revolution might have taken decades or centuries longer. The whole trajectory of human intellectual history might have been different. And every single scientific advance that came after, from Newton's laws of motion to the Industrial Revolution to spaceflight to the internet to the device you're watching this on, kind of traces back to that moment when Galileo looked through his telescope and saw Venus go through phases. We owe Venus. In a real, historical, tangible sense, we owe Venus a debt for the whole modern world, which is a wild thought when you consider that Venus itself, the planet, doesn't care. It's just sitting there, cooking, being hell. It didn't know it was going to overthrow the Aristotelian cosmos. It didn't know it was going to catalyze the scientific revolution. It was just doing its thing. And we, down here on Earth, made meaning out of it. I want to tell you about another Venus-related event that shaped human history in a way most people don't know about. The transits of Venus. A transit of Venus happens when Venus passes directly between Earth and the Sun, so that we can see Venus as a small black dot moving slowly across the disk of the Sun. It's a beautiful, rare event. Because of the way the orbits are tilted, transits of Venus happen in pairs, 8 years apart, and then there's a gap of over a century before the next pair. The last transits of Venus in our lifetime were in 2004 and 2012. The next pair won't happen until 2117 and 2125, which means, statistically, most people watching this will never see one. If you saw the 2012 transit, congratulations. You were one of the lucky ones. But here's the thing. In the 18th century, transits of Venus were a really big deal because they offered the only known way to measure the size of the solar system. Astronomers had figured out the relative distances between planets using Kepler's laws, but they didn't know the actual absolute distances. They knew Mars was, say, 1.5 times as far from the Sun as Earth, but they didn't know how far Earth itself was from the Sun. And without that fundamental number called the astronomical unit, you couldn't calculate anything else in absolute terms. Edmund Halley of Halley's Comet fame realized in the early 1700s that a carefully timed observation of a Venus transit from multiple locations on Earth could, through a bit of parallax calculation, give us the actual value of the astronomical unit. It was a clever solution to a fundamental problem. The idea was this: if you observe the transit from different latitudes on Earth, Venus would appear to trace a slightly different path across the Sun's disk from each location. By measuring the difference between these paths, you could calculate the parallax angle. And from the parallax angle, using some straightforward trigonometry, you could figure out the actual distance from Earth to the Sun. Halley knew he wouldn't live to see the next transit. It was going to happen in 1761, and he'd be long dead by then. But he wrote up his plan, published it in 1716, and essentially set a homework assignment for the next generation of astronomers. Please, when the transit comes, send observers to as many places on Earth as possible. Take the measurements. Calculate the astronomical unit. Do this for me. I won't be here to see it. And they did. They actually did. The 1761 transit of Venus prompted one of the most extensive international scientific collaborations in human history up to that point. Astronomers were dispatched from Britain, France, Sweden, Russia, and elsewhere to locations all over the world. Some traveled to Siberia, some to the Cape of Good Hope, some to India, some to Newfoundland, some to Tahiti, although that one actually happened during the 1769 transit, not the 1761 one. Let me come back to that in a second. These journeys were brutal. This was the 18th century. Sailing across oceans took months. There were storms, shipwrecks, diseases, wars. The Seven Years' War was happening at the same time as the 1761 transit, which meant that scientific expeditions were getting caught up in naval battles. There's this story about the French astronomer Guillaume Le Gentil, who set out for India to observe the 1761 transit, and his ship got diverted by the war, and he arrived at his destination just after the transit had already happened, missed it entirely. But he was a determined guy. He decided, well, there's another transit in 1769, only 8 years away. I'll just stay out here in the Indian Ocean and wait for it. So he spent 8 years wandering around the Indian Ocean, making observations of other things, waiting for 1769. When the 1769 transit finally happened, he was in Pondicherry, all set up, telescope ready, and it was cloudy. Just cloudy on the one day of the century when he needed it not to be cloudy. He'd wasted 8 years of his life waiting for a moment that lasted a few hours and got obscured by clouds. He was so devastated that he essentially had a nervous breakdown. He tried to sail home to France, got sick on the way, was shipwrecked, arrived home 11 years after he had left, and discovered that his relatives, assuming he was dead, had divided up his estate. His wife had remarried. He'd been declared legally deceased. He had to sue to get his own life back. The Le Gentil story is one of the most tragic in the history of science. It's what happens when you dedicate yourself to a scientific observation and the universe just kind of laughs at you. But it also illustrates how much these people were willing to sacrifice. He gave 11 years of his life, essentially threw them away, in the hopes of contributing a single data point to humanity's understanding of the solar system. Other observers had better luck, and by combining data from dozens of locations, astronomers did manage to calculate the astronomical unit. Their answer was about 153 million kilometers, which was pretty close to the modern value of about 149.6 million kilometers, off by a few percent, but close enough to be a genuine achievement. The 1769 transit was even more ambitious, with more expeditions, more observers, more careful preparation. And the most famous expedition of that year was Captain James Cook's voyage to Tahiti. You know Captain Cook, everybody knows Captain Cook, but most people don't know that his first great voyage, the one that made him famous, was originally a scientific mission to observe the transit of Venus. The British government funded Cook's expedition specifically to send astronomers to Tahiti to observe the 1769 transit. Tahiti was chosen because it was in the southern hemisphere, and observations from there would complement observations from the northern hemisphere, giving a better baseline for the parallax calculations. Cook's ship, the HMS Endeavour, was outfitted with astronomical instruments, and he had an astronomer aboard named Charles Green. They successfully observed the transit on June 3rd, 1769, and then, after the transit, Cook opened his sealed secret orders, which had been given to him by the Admiralty, and those orders instructed him to search for the mysterious southern continent that was theorized to exist somewhere in the South Pacific, which is what led to his charting of New Zealand and the eastern coast of Australia. So, kind of astonishingly, the entire course of Pacific exploration by the British, the eventual colonization of Australia and New Zealand, and all the political and cultural consequences that flowed from that were kicked off by a mission to observe the transit of Venus. Venus, again, changing history, not by anything Venus did, but by the excuse it provided for humans to do wildly ambitious things. The transits of Venus in the 1800s continued to attract enormous scientific attention, The 1874 and 1882 transits inspired huge international efforts, with photographic technology now available for the first time. Astronomers took thousands of photographs trying to time the exact moments when Venus's disk touched the edge of the sun. They still had a lot of trouble getting precise measurements because of an optical phenomenon called the black drop effect, where Venus's disk appears to smear or connect to the edge of the sun in a way that makes exact timing difficult. But they got better and better data with each transit. By the 20th century, we had other methods for calculating the astronomical unit, and transits of Venus lost their scientific importance. But they remained beautiful, rare events, occasions for humans everywhere to look up together and marvel at the mechanics of the solar system. I watched the 2012 transit. I want to tell you about it briefly because it was one of the most meaningful astronomical experiences of my life. I was in a park with a bunch of other amateur astronomers who had brought telescopes with solar filters. I looked through one of the telescopes, and there it was, a tiny, perfect black circle moving slowly across the face of the sun. Just a dot, almost nothing, and also everything, because that dot was Venus, the planet I had been reading about my whole life, the planet that had inspired Galileo, that had triggered 11-year odysseys of failed observation, that had guided Captain Cook to Tahiti, that had been the goddess of love in 100 cultures. And there it was, moving across the sun, and I could see it with my own eyes in real time. I remember standing back from the telescope, looking up at the sun, and thinking about the fact that if I had somehow perfect vision, I would be able to see Venus with my naked eye, even against the sun's glare. It was that close, that present, that real. And in 100 years or so, when the next transit happens, other people will look up at the sun and see Venus, and I won't be there anymore. But Venus will be, and so will the sun. And humans will still be watching if we're around at all, passing the observation down through the generations, one transit at a time. That's a lot to feel while looking through a telescope in a park. But I felt it, and I stand by it. Okay, let me shift topics again because I want to talk about the atmosphere of Venus in more detail. Really deep detail, because it's genuinely one of the most complicated and fascinating atmospheres in the solar system, and I feel like I've been kind of glossing over it. The atmosphere of Venus is divided into several layers, each with its own personality. Let me walk you through them from top to bottom, like we're descending in a spacecraft. At the very top, above about 250 kilometers altitude, is the exosphere. This is where the atmosphere thins out into space. It's incredibly tenuous up here, just occasional atoms and molecules floating around. But it's important because this is where atmospheric loss happens, where the solar wind strips away lighter elements, where Venus, over billions of years, has been slowly bleeding into space. Below the exosphere, from about 120 to 250 kilometers, is the thermosphere. This is where solar radiation heats the atmosphere directly. Temperatures here can vary wildly between day and night. On the day side, it can be quite hot, several hundred degrees. On the night side, it can be extremely cold, well below zero. This day-night temperature difference is one of the weirdest things about the upper atmosphere of Venus, because down at the surface, it's basically the same temperature everywhere, day or night. But up in the thermosphere, there's this huge asymmetry. Between about 100 and 120 kilometers, there's a layer called the mesosphere. This is where the atmosphere is at its coldest. Temperatures drop below minus 100 degrees Celsius, which is kind of hilarious considering that 100 kilometers below, at the surface, it's over 470 degrees. Venus has this bizarre thermal profile where the coldest layer of its atmosphere is sandwiched between much hotter layers above and below. It's like a temperature inversion of epic proportions. Below the mesosphere, from about 50 to 100 kilometers, is where the main cloud deck lives. And this is the part of the Venusian atmosphere that I find most interesting, so I want to really dig into it. The cloud deck of Venus is not one uniform blanket. It's actually 3 distinct layers, each with its own composition and behavior. There's an upper cloud layer from about 70 to 90 kilometers, a middle cloud layer from about 50 to 70 kilometers, and a lower cloud layer from about 47 to 50 kilometers. And below the clouds, there's a haze layer extending down to about 30 kilometers. The clouds are made primarily of sulfuric acid droplets, not water. Sulfuric acid, which is one of the most corrosive substances known. If you put a drop of sulfuric acid on your skin, it would burn you. If you filled a swimming pool with sulfuric acid and jumped in, well, you wouldn't come out. The clouds of Venus are basically an ocean of the stuff floating in the sky. But here's the weird part. The clouds aren't pure sulfuric acid. There's a mysterious component that makes them absorb ultraviolet light in a distinctive pattern. This is the UV absorber I mentioned earlier. And after decades of study, we still don't know what it is. It could be iron chloride. It could be sulfur allotropes. It could be, and this is the fun speculation, some kind of biological pigment produced by microorganisms living in the cloud droplets. The idea that there might be life in the clouds of Venus is not new. Carl Sagan and Harold Morowitz wrote a famous paper about it in 1967, arguing that the middle cloud layer of Venus has conditions that are, all things considered, not that hostile to life. The temperature there is between about 0 and 60 degrees Celsius, which is comparable to Earth's surface. The pressure is roughly 1 Earth atmosphere. There's sunlight for photosynthesis. There's water, admittedly not much, but some. And there are nutrients, including sulfur compounds that certain kinds of extremophile bacteria on Earth are known to metabolize. If life ever existed on the surface of Venus, back when it was habitable, and if some of that life adapted to survive as the surface became uninhabitable, the cloud deck would be the natural refuge. It's the only place on Venus where liquid water can even theoretically exist, in the form of tiny droplets absorbed into the sulfuric acid mixture. It's the only place where the temperature is compatible with organic chemistry as we know it. It's the only place where you could have anything resembling Earth biology. And so, for the last 50 years, there's been this persistent minority view among astrobiologists that we should be looking for microbial life in the Venusian clouds. That it's plausible, that it's testable, that it's worth taking seriously. The 2020 phosphine controversy really lit up this whole line of thinking. Because phosphine, if it was really there, and if it wasn't being produced by some unknown non-biological chemistry, would be a very strong indicator of life. Phosphine on Earth is produced by anaerobic bacteria, the kind that live in swamps and marshes and the intestines of animals. It's a smelly, toxic gas. But it's also kind of a biosignature. When you find phosphine on a rocky planet, it's hard to explain without invoking biology. The initial announcement in September 2020 was made by a team led by Jane Greaves at Cardiff University. They had used 2 different telescopes, the James Clerk Maxwell Telescope in Hawaii and the ALMA array in Chile, to detect a specific spectral signature that matched phosphine. They found it in the middle cloud deck of Venus at concentrations of about 20 parts per billion, which sounds tiny, but it's actually way more phosphine than any known non-biological process could produce. The paper made global headlines. Life on Venus was the tabloid version. The actual scientific claim was more measured. They said, "We've detected phosphine. We can't explain it with any known chemistry. We're not saying it's life, but we can't rule out life, and this deserves further investigation." The scientific community reacted. Some researchers were excited, others were skeptical. And over the next several months and years, there was a whole back and forth of new analyses, reanalyses, and counter-analyses. Some teams tried to reproduce the phosphine detection using different techniques and got no signal. Others said the original data processing had introduced artifacts. Still others said, actually, there is phosphine just at lower concentrations than initially claimed. The current state of the phosphine question is unresolved. There's a signal in the data. Something is there. But whether it's phosphine or a similar molecule like sulfur dioxide masquerading as phosphine or an artifact of data processing is still being debated. Various instruments have gotten different results. And here's the thing, even if there is phosphine, that doesn't necessarily mean there's life. There could be some exotic non-biological chemistry that we haven't figured out yet. Volcanic processes, perhaps, photochemical reactions in the clouds, lightning strikes producing unusual compounds. Any of these could, in theory, produce phosphine. We just don't have good models for them, so we can't rule them in or out with confidence. The only way to really resolve the question is to send a probe to Venus that can directly sample the cloud atmosphere and look for phosphine, and for other potential biosignatures, and for anything that might indicate biological activity, which is one of the reasons the upcoming Da Vinci mission is so exciting. It's specifically designed to drop through the atmosphere and make direct measurements of what's really there. I think about the phosphine controversy a lot, actually, not just because of what it might mean for life on Venus, but because of what it revealed about how science works when the stakes are high and the evidence is ambiguous. There was so much drama, so many competing papers, so much media coverage. Every new result was breathlessly reported. Every new counter-result was reported with equal breathlessness. And the actual scientific truth, whatever it is, kept receding as the debate got more heated. Science is supposed to be dispassionate and objective. But scientists are people. And people get excited about the possibility of finding alien life. And when you get excited, you sometimes see things in the data that aren't there. And when someone else says the thing you're excited about isn't there, you sometimes get defensive, and the whole process gets messy. But it also works slowly, over time. Even with all the noise, the truth tends to emerge. The phosphine question will eventually get answered, either by a direct probe or by better remote observations. And when it does, we'll know, one way or the other, whether there's life in the clouds of Venus. And that answer will be one of the most consequential facts humanity has ever learned. Either we're not alone, or we are, at least in this solar system. Either way, everything changes. I want to keep going with the atmosphere for a bit, because I haven't even gotten to the surface yet in this descent I'm doing. Below the clouds, from about 30 to 47 kilometers, is a clear region. No clouds, just thick, hot carbon dioxide gas with traces of sulfur compounds. As you descend through this layer, the temperature climbs steadily. At the top of it, it's still relatively pleasant, maybe 100 degrees Celsius. By the bottom, it's already over 400 degrees. The pressure is also climbing from about half an atmosphere at the top to about 10 atmospheres at the bottom, And below 30 kilometers, you're in what we might call the deep atmosphere. This is the layer that behaves almost more like a fluid than a gas. The carbon dioxide down here is what's called supercritical, which means it's at a temperature and pressure high enough that the distinction between gas and liquid stops making sense. It's neither one, it's both. It's a strange, dense, hot medium that flows and swirls in ways that gases at normal pressures don't. When the Venera probes descended through this layer, they experienced buoyancy effects that were significantly different from what a probe would experience descending through Earth's atmosphere. The dense supercritical CO2 pushed back against them, slowed their fall, and transferred heat into their structures at rates that were hard to model precisely. By the time you reach the surface, the atmospheric pressure is about 92 times what it is on Earth, which, as I mentioned before, is equivalent to being about 900 meters underwater. And the atmosphere at surface level is so dense that sound travels differently through it. If you were standing on the surface of Venus and you clapped your hands, the sound would be deeper and would travel farther than a clap on Earth, because the dense atmosphere carries sound better. Voices, if humans could somehow stand on Venus, which we absolutely cannot, would sound bizarre, deeper, slower to travel over distances, kind of thick and syrupy, like everyone was talking through a heavy blanket. Some acousticians have tried to model what human speech would sound like on Venus, and their conclusion is that we would sound kind of like we were speaking underwater while also having a very bad head cold. It's not a flattering sound profile. Winds at the surface of Venus are counterintuitively quite slow, just a few kilometers per hour at most, which sounds calm. But because the atmosphere is so dense, even a slow wind at the surface would feel like a strong current of water pushing against you. It's the difference between a breeze blowing on you in a park and standing in a river. Same speed of motion, very different feeling. Anything the winds pushed around at the surface would move slowly but with tremendous force. There's a whole area of study around Venusian surface aeolian processes, which is the technical term for what wind does to a planet's surface. On Venus, the wind might be slow, but over geological time, it moves dust and small particles around, sculpts features, and gradually alters the landscape. There are dune fields on Venus. Photographs from the Magellan orbiter using synthetic aperture radar to see through the clouds showed extensive dune fields in some regions, which means Venus has sort of deserts, not like Earth deserts, obviously, but large expanses of wind-shaped terrain that are functionally analogous to deserts. The particles that make up these dunes aren't sand as we know it. They're probably fine-grained volcanic material, ground down by whatever processes operate on the Venusian surface. Okay, I want to take a break from the atmosphere and talk about the surface itself now, because we've been dancing around the geology of Venus, but there's a lot more to say about it. Venus has a fundamentally different geology from Earth, and that difference is one of the most important and least appreciated facts about our neighbor planet. On Earth, we have plate tectonics. The lithosphere, which is the rigid outer shell of the planet, is broken into large pieces called plates, and these plates move around slowly, driven by convection currents in the mantle below. Where plates collide, you get mountain ranges. Where they pull apart, you get rift valleys and mid-ocean ridges. Where one plate dives beneath another, you get subduction zones with earthquakes and volcanic arcs. This entire process is how Earth releases its internal heat and how it recycles its crust. Venus does not have plate tectonics. As far as we can tell, the entire lithosphere of Venus is a single, unbroken shell. It doesn't move around in pieces. It doesn't have subduction zones. It doesn't have mid-ocean ridges, both because it doesn't have oceans and because it doesn't have the tectonic activity that would form them. So how does Venus release its internal heat? This is one of the great mysteries of Venusian geology, because Venus is roughly the same size as Earth, made of roughly the same materials, and formed at roughly the same time. It should have a comparable amount of internal heat. That heat has to go somewhere. On Earth, it comes out gradually, continuously through plate tectonics. On Venus, it comes out differently. The current best hypothesis is that Venus undergoes what geologists call catastrophic resurfacing events. Every 500 million years or so, more or less, the entire surface of Venus gets replaced. Massive planet-wide volcanic eruptions burst forth, covering the whole surface with fresh lava. The old surface gets buried or melts or breaks up, and a new surface forms. And then, for the next few 100 million years, that new surface sits there, slowly heating up from below, until finally the pressure builds up enough to trigger another catastrophic resurfacing. We think this is the case because the surface of Venus, as mapped by the Magellan mission, is unusually uniform in age. The crater counts, which are how planetary scientists estimate the age of a surface, suggest that most of Venus is about the same age, roughly 500 million years old, which is really weird. Because on other planets and moons, you tend to see a range of ages, old regions and young regions next to each other. Venus is just kind of all one age everywhere. The catastrophic resurfacing hypothesis is elegant, but it's also unsettling, because it means Venus goes through these apocalyptic episodes where the entire planet basically melts. Everything on the surface gets destroyed, every feature erased, every trace of previous geology buried under fresh lava. And this happens periodically throughout the history of the planet, which raises a disturbing question. If Venus was ever habitable back in its early history, and if life ever existed there, would we be able to find evidence of it, or would the resurfacing events have destroyed all traces? The answer is complicated. If life existed on the surface of Venus billions of years ago, and if that surface has been recycled multiple times since then any fossils or geochemical traces are probably gone, buried deep in the mantle, or turned to vapor, or so thoroughly transformed that we couldn't identify them as biological in origin. But if any of that life migrated to the clouds and adapted to survive there, it might still be around, untouched by the surface catastrophes. Because the clouds don't get resurfaced. They just keep circulating generation after generation in the same layers of the atmosphere, isolated from the geological chaos below. So the search for life on Venus, if it happens, has to focus on the clouds, not because life couldn't have started elsewhere, but because the clouds are the only place where anything living would still be findable. Let me tell you about some specific features on the Venusian surface, because I don't want this to be all abstract. Venus has actual specific mappable landscapes, and some of them are really weird. There's a region called Ishtar Terra up in the northern hemisphere. It's a highland region roughly the size of Australia, and it contains the Maxwell Montes, which is the tallest mountain on Venus. Maxwell Montes is about 11 kilometers tall, which is significantly taller than Everest. It's also named, incidentally, after the Scottish physicist James Clerk Maxwell, and it's one of the very few features on Venus not named after a woman. The convention for naming features on Venus is to use female names, mostly, goddesses, mythological figures, notable historical women. Maxwell Montes is a holdover from an earlier naming convention and just kind of got grandfathered in. There's another highland region called Aphrodite Terra, which straddles the equator. It's much larger than Ishtar Terra, roughly the size of South America, and it has all kinds of interesting features, including deep canyons and complex ridge systems. And scattered across the plains of Venus, there are these features called coronae. Nothing like them exists on Earth. They're roughly circular structures, ranging from a few hundred kilometers to over 1,000 kilometers across, with concentric rings of fractures and ridges around them. They're thought to be formed by rising plumes of hot magma from the mantle, which push the crust up into a dome, and then the dome collapses when the magma cools. What's left is this weird ring-shaped scar on the surface. There are hundreds of these coronae on Venus. Some are ancient, some may still be active. In fact, one of the most exciting recent findings from reanalyzed Magellan data is evidence that at least a few coronae have been active in the last few decades, meaning active on the timescale of human observations, which means Venus is not a dead planet geologically. It's still doing things. Slowly, occasionally, but it's doing them. Then there are the pancake domes I mentioned earlier. These are flat-topped, roughly circular domes, tens of kilometers across, that appear to be formed by very viscous lava. Kind of like if you poured really thick syrup onto a table and let it spread out. On Earth, you don't see features like this because our atmosphere doesn't provide enough back pressure to keep viscous lava from flowing further. But on Venus, the dense atmosphere pushes back against the erupting lava, so it piles up in these flat, dome-like structures and then hardens in place. There are also features called arachnoids because they look like giant spiders when photographed from orbit. They're circular fracture patterns with radial fractures spreading outward, like the legs of a spider. Nobody is entirely sure how they form. They might be smaller cousins of the coronae, made by the same kind of magmatic uplift, but at a smaller scale. And there are the tesserae, which are highly deformed regions of terrain that look, from orbit, like crumpled fabric. Ridges and grooves crossing each other in complex patterns. The tesserae are thought to be some of the oldest surviving terrain on Venus, possibly dating from before the last catastrophic resurfacing event. If we're going to find any evidence of Venus's ancient past, evidence of what the planet was like when it might have been habitable, the tesserae are probably where we'll find it. They're geological time capsules, if any exist on Venus at all. The upcoming Veritas mission is specifically designed to map the tesserae in high resolution and try to figure out what they're made of. If they contain minerals that require water to form, like granites, that would be a huge deal. Because granites on Earth form primarily in the presence of water. If Venus has granitic tesserae, that would be strong evidence that Venus had liquid water on its surface at some point in the past, which would support the hypothesis that Venus was once habitable before the runaway greenhouse effect turned it into what it is now. I want to talk about that transition, the moment, or rather the long, slow process when Venus went from being potentially habitable to being the hellscape it is today. Because this is arguably the most important scientific question that Venus can help us answer, and it has direct relevance to the future of Earth. Here's the current best guess at what happened. 4.5 billion years ago, Venus and Earth formed at more or less the same time from more or less the same materials in similar orbits. Both planets had thick atmospheres. Both planets had oceans, probably. Both planets had active volcanism. Both planets were young and hot and geologically dynamic. For the first billion years or so, Venus and Earth may have been remarkably similar. Some models suggest that Venus had liquid water oceans for as long as 2 billion years, which is longer than it took life to emerge on Earth. If those Venusian oceans existed, and if the conditions were right, life could have started there. Maybe, we don't know, but it's not implausible. Then gradually, things started to change. The sun, which was fainter when it was young, started to brighten as it aged. This is normal stellar evolution. Stars get brighter over time as they burn through their hydrogen. And as the sun got brighter, Venus, being closer to the sun than Earth, started to warm up faster than Earth did. At some point, and we don't know exactly when or how quickly, Venus crossed a threshold. The temperature got high enough that ocean water started evaporating faster than it was being replenished. Water vapor is a powerful greenhouse gas, so as more water evaporated, the atmosphere trapped more heat, which caused more water to evaporate, which trapped more heat. Runaway feedback loop. Positive feedback in the technical sense, disastrous in the practical sense. Eventually, all of Venus's ocean water made it into the atmosphere, which was a lot of water, enough water to blanket the planet in a thick, hot, humid atmosphere. And then things got worse, because in the upper atmosphere, water molecules got broken apart by ultraviolet radiation from the sun. The hydrogen atoms, being light, escaped into space. The oxygen atoms, being heavier, mostly stayed behind, but eventually got sequestered into rocks and minerals through oxidation reactions. Over time, Venus lost essentially all of its water. It's the great tragedy of Venus. A planet that once had oceans that might have hosted life was slowly and thoroughly desiccated by a combination of solar brightening and hydrogen escape. What's left today is a planet with almost no water at all. The atmosphere contains only trace amounts of water vapor. There's no water on the surface. There's very little water even bound up in the rocks and minerals. Venus is dry, bone dry, desperately, catastrophically dry. And once the water was gone, other feedback processes kicked in. Volcanic activity kept pumping carbon dioxide into the atmosphere. On Earth, we have this thing called the carbonate-silicate cycle, where CO2 gets scrubbed out of the atmosphere by reactions with silicate rocks in the presence of liquid water, forming carbonate minerals that get buried and eventually recycled through plate tectonics. This cycle regulates Earth's climate over long timescales. It's a big part of why Earth has stayed habitable for so long. But on Venus, without liquid water, the carbonate-silicate cycle broke down. CO2 kept accumulating in the atmosphere with no way to remove it, and the atmosphere kept getting thicker and thicker until it reached the crushing 92 atmospheres we see today. And the temperature kept climbing until it stabilized at the current infernal levels. The whole process from potentially habitable Earth-like planet to modern-day Venus probably took hundreds of millions of years. It wasn't sudden, nothing catastrophic in the geological sense, just slow, inexorable warming over timescales longer than the entire history of complex life on Earth. Now here's the part that keeps me up at night, because Earth is also getting warmer. And while nobody serious is saying that Earth is going to turn into Venus, in the near future, or even in the medium future, the fundamental physics of runaway greenhouse effects is the same on both planets. Once you push a planetary climate past certain thresholds, positive feedback loops can take over, and things can escalate in ways that are very difficult to reverse. Venus is a warning. Not a warning that we're headed for the same fate, but a warning that planetary climates can change dramatically, catastrophically, and permanently when the right conditions are met. That the difference between a habitable world and a hellscape isn't as large as we might like to think. That the biosphere we depend on is contingent and precious and could be lost. Studying Venus, understanding exactly how and when and why it lost its habitability is one of the most important things planetary science can do for humanity. Because we don't have great models of climate feedback at extreme temperatures. We can't run controlled experiments on planets. but we have Venus sitting right next door as a case study of what happens when things go wrong. If we can understand Venus's transformation in detail, we might be able to build better models of what could, in theory, happen to Earth, and use those models to inform decisions about how we manage our own climate. Which brings me back to why I care about Venus so much. It's not just that it's interesting. Although it is, it's that Venus has lessons to teach us that we can't learn anywhere else about planetary evolution, about climate, about the fragility of habitability, about the fact that being in the habitable zone of a star isn't a guarantee of anything. Earth and Venus are both in the habitable zone. One of them is a paradise, the other is a nightmare. And the difference between them is something we're still trying to understand. Okay, I'm going to stop being heavy and get back to some lighter stuff. Let me tell you about some of the weirdest, most speculative ideas about Venus that have been proposed over the years. Not because these ideas are necessarily true, but because they're fun. And they illustrate how much room there still is for wild thinking about our neighbor planet. Idea number one, Venus has floating creatures in its clouds, not microbes, full-on macroscopic floating organisms. This idea has been kicked around in various forms since the mid-20th century. The most recent serious version I've seen came from a paper suggesting that if life did adapt to the Venusian cloud environment, it might have evolved into something like giant, translucent, jellyfish-like creatures, floating in the middle cloud layer, feeding on chemical compounds, drifting on the winds. Is this likely? No. Probably not. But is it impossible? Also no. The middle cloud layer of Venus is stable enough and rich enough in interesting chemistry that if life existed there, and if it had a couple billion years to evolve, it could potentially get pretty complex. There's no fundamental physical reason why cloud-dwelling organisms couldn't develop. There's just no evidence so far that they did. Idea number two, Venus is being visited or was visited in the past by extraterrestrial civilizations, and they built structures there that we might be able to detect. This is very much fringe stuff. There's no evidence for it. But every so often, someone points at a weird feature in the Magellan radar images and says, hey, that looks kind of artificial. And then someone else looks at it and says, no, that's just a natural geological formation. And the discussion moves on. But the images are grainy enough and Venus is unexplored enough at high resolution that you can't definitively rule out the possibility of unusual features, which is a low probability but non-zero situation that some people find compelling. Idea number three, Venus is going to slow down its rotation even more and eventually start rotating backwards. This one is actually not fringe science. It's a serious hypothesis that some planetary scientists have proposed. Venus already rotates in the opposite direction from most of the other planets. This is called retrograde rotation, and it rotates extremely slowly. A day on Venus is longer than a year on Venus, but there are some models suggesting that Venus's rotation might be actively slowing down further due to tidal interactions with the sun's gravity and with the thick atmosphere. If those models are correct, then Venus might, at some point in the distant future, stop rotating entirely, or start rotating in the other direction, which would have huge consequences for the atmospheric circulation patterns and probably for the surface temperature distribution as well. But this is all very speculative and would happen on timescales of hundreds of millions to billions of years. So it's not something anyone needs to worry about personally. Idea number four, Venus was hit by a giant object early in its history, and that impact is what caused its retrograde rotation and its strange lack of a moon. This is a real hypothesis that gets discussed in planetary science circles. The idea is that when Venus was young, it may have been struck by a large body, similar to the impact that formed Earth's moon. But instead of ejecting material to form a moon, the impact on Venus was oriented differently, and it just flipped the planet's rotational axis, which is why Venus rotates backwards and why it doesn't have a moon. This is called the impact hypothesis for Venus's rotation, and it's not universally accepted, but it's a serious contender for explaining these weird features. Idea number 5, and this is one of my personal favorites. Venus might have plate tectonics, but of a different kind than Earth's. Some recent research suggests that Venus doesn't have the kind of plate tectonics we have on Earth, where large plates move around and interact at their boundaries. But it might have something called squishy lid tectonics, where the crust is broken into blocks that jostle against each other and slowly rearrange themselves. Or it might have episodic tectonics, where long periods of tectonic quiet are punctuated by brief periods of intense activity. Or it might have something even weirder, some form of crustal recycling that doesn't fit any of our existing models. The point is, we don't really know how Venus's interior behaves. Our models of planetary interiors are based mostly on Earth, with some data from Mars and the Moon. Venus is different enough that our models might not apply directly, and the closer we look, the more likely it seems that Venus has its own unique way of being a planet, not just a broken version of Earth, not just a hotter version of Earth, but its own thing. Idea number 6. The clouds of Venus might be electrically active in ways that are more dramatic than we currently understand. There's some evidence going back to the Venera missions that Venus has lightning. And more recent observations from the Venus Express spacecraft and from Earth-based instruments have detected electromagnetic signals that are consistent with lightning discharges in the clouds. If Venus does have frequent lightning, that could have huge implications for the chemistry of the atmosphere. Lightning strikes can produce all kinds of unusual compounds, including some that might mimic biological signatures. This is one of the alternative explanations for the phosphine detection, actually. Maybe there's a lot of lightning in the Venusian clouds, and that lightning is producing compounds we don't fully understand, and one of those compounds is showing up in our data as a phosphine-like signature. Idea number 7. Venus might be a good place to test technologies for interstellar exploration. This one is fun because it flips the usual narrative. Usually people talk about Venus as if it's an obstacle to overcome, a place too hostile to visit. But the extreme conditions on Venus, the heat, the pressure, the corrosive chemistry, are actually similar to conditions we'd expect to encounter on many exoplanets. If we can build robots that can survive on Venus, we're building the same kinds of robots we'd need to send to hot super-Earths orbiting other stars. So Venus is, in a way, a testing ground, a place to develop technologies that will let us explore worlds far beyond our solar system, which reframes Venus from a problem to a resource. Okay, I've been going for a while now. Let me try to wrap some of this up with some final thoughts about what Venus means, or what it could mean if we let it. Here's the thing about Venus. It's the planet closest to us, physically closest. When Venus is on our side of the sun, it's about 40 million kilometers away, which is roughly 100 times farther than the Moon, but still much closer than Mars, which averages around 225 million kilometers, or any of the outer planets. Venus is our neighbor, our next door neighbor, and we've kind of ignored it. Not entirely. We've sent probes, we've mapped it, we've studied it from Earth. But compared to Mars, which has become the darling of solar system exploration, Venus has been neglected. There are more spacecraft actively operating on Mars right now than there have ever been on Venus in total, over the entire history of exploration. Mars has rovers driving around, taking selfies, drilling into rocks. Venus has nothing. A few orbiters from various nations, but nothing on the surface. Nothing in the atmosphere. Just cold, dead spacecraft, buried under fresh lava or crushed into unrecognizability, spread across the surface of a planet nobody visits anymore. This is going to change in the next decade. We have Da Vinci coming in the late 2020s or early 2030s, which will drop a probe through the atmosphere and make detailed measurements all the way down to the surface. We have Veritas, which will map Venus at higher resolution than ever before and try to determine the composition of the surface materials. We have Envision, the European Space Agency's Venus orbiter, which will do complementary science. We have private companies like Rocket Lab proposing their own Venus missions. We have plans for future landers, atmospheric balloons, sample return missions. It's a Venus renaissance. And it's about time. I hope, and I really do hope, that the next generation of Venus exploration will bring the same kind of public excitement that Mars exploration has enjoyed for the last 20 years. I hope that when the Da Vinci probe drops through the Venusian atmosphere and starts transmitting data from inside the clouds, the world will pay attention. I hope kids will grow up wanting to be Venus scientists. I hope there will be nail-biting live coverage of the descent, like there was for Curiosity's 7 Minutes of Terror on Mars. Because Venus deserves that. Not because Venus is prettier than Mars, or more habitable, or more likely to have life, but because Venus is important, and close, and weird, and unfinished. There's so much we don't know about it, so many mysteries, so many potential surprises, and every mission we send has the chance to teach us something fundamental about how planets work, and how climates evolve, and how our own future might unfold. I want to end this by telling you what I hope, not what I predict, not what I expect, just what I hope. I hope we find life in the clouds of Venus. I hope it's microbial and simple and unmistakable. I hope we can watch these Venusian microbes under a microscope one day and marvel at how different or how similar they are to life on Earth. I hope they teach us that biology can survive in places we thought were impossible, that the universe is more crowded with life than we currently believe. I hope we understand what happened to Venus's water, not just theoretically, but in detail. I hope we can trace the exact chain of events that turned Venus from a watery world into a desert. And I hope those lessons help us protect our own water, our own oceans, our own precious temperate blue planet. I hope someday humans visit Venus. Not the surface, obviously, but the clouds. I hope we build those floating cities that Havoc dreamed about. I hope people live there, at least for a while. Scientists and their children floating in the upper atmosphere of Venus, doing research, sending back data, watching the sun rise and set through orange hazes. I hope Venus becomes a place, not just a distant object, but a place where humans have been. I hope if there's anything left of Venus's ancient history, if the tesserae hold any secrets from the time before the runaway greenhouse, that we find them. I hope we can piece together the story of Venus's first billion years, whether there was life, whether there were oceans, whether Venus was, for a while, a garden. And I hope, most of all, that we keep looking up, that we keep sending robots to distant worlds, that we keep asking questions, that we don't lose the curiosity that drove the Venera engineers to build spacecraft that could survive in hell, that we don't lose the ambition that sent Captain Cook to Tahiti to watch a black dot cross the sun, that we don't lose the wonder that made ancient Sumerians name Venus after their most important goddess. because we're small, we're temporary, we're stuck on this one planet, at least for now, and the universe is big, and most of it is not habitable for creatures like us. But some of it is, or might have been, or could be again. And every clue we can find, every question we can answer, every mystery we can solve brings us a little closer to understanding our place in all